Hello and welcome to Space Historians. I'm so glad you've found your way here tonight, ready to let the day fall away and drift into something quieter, something vast. Tonight, we're not going to rush through the cosmos. We're going to float gently, slowly, into one of the most overlooked mysteries of our galactic home. Before we begin, take a moment. Where are you right now? Maybe you're lying down, the lights dimmed, the world outside fading to a gentle hum. Maybe you're somewhere far from where I am, in a different time zone, where the sun is just beginning to rise or the stars are just appearing. Wherever you are, you're inside the Milky Way. Every breath you take, every thought that crosses your mind, it all happens within a galaxy that stretches 100,000 light years across. But here's something we rarely consider. We always imagine the galaxy as flat, like a disk spinning through space. And it is, mostly. But what about up? What about down? What lies in those directions perpendicular to the familiar spiral we know so well? If you enjoy these quiet journeys through space and time, a like and a subscribe help this channel continue its gentle orbit through the cosmos. And for those who've already joined this constellation of curious minds, thank you. You're part of this voyage. Tonight, we're going to explore the vertical dimension of our galaxy. Not outward toward its edges, but upward and downward into regions most people never think about. Above and below the flat disk of stars, there are structures so enormous they dwarf the spiral arms. There are ancient stars drifting in isolation. There are bubbles of energy blown by forces at the galactic center. There are mysteries that change everything we thought we knew about where we live. Most maps of the Milky Way show it edge-on, a thin, bright line across the darkness. But if you could step outside it, if you could float above or below its plane, you'd see something entirely different. You'd see depth. You'd see layers. You'd see that the galaxy extends far beyond its bright disk, reaching into space above and below like an invisible atmosphere. So settle in. Let your breathing slow. Let your thoughts drift weightlessly. Tonight, we're going to travel in a direction most people never consider. We're going up and we're going down through the hidden dimensions of our galactic home. There's a light shining above our galaxy that most people will never see. Not because it's too faint or too far away, but because it's invisible. It doesn't glow in the wavelengths our eyes can detect. It shines in gamma rays, the most energetic form of light in the universe, the kind of radiation that comes from the most violent cosmic events. And this light doesn't come from some distant explosion or faraway quasar. It comes from directly above our heads, from a structure so enormous that it towers 25,000 light years into space. And below us, beneath the plane of the Milky Way's disk, there's another one, a mirror image, equally vast, equally mysterious. Together, they form something that shouldn't exist. Two massive bubbles of glowing energy, reaching upward and downward from the heart of our galaxy, each one large enough to contain thousands of solar systems, each one bright enough to outshine everything around it. If only we could see gamma rays with our naked eyes. For most of human history, we didn't know they were there. We couldn't. The light they emit passes right through our atmosphere without leaving a trace we can perceive. It took a specialized telescope, launched into orbit above Earth's protective blanket, to finally reveal them. And when they were discovered in 2010, they changed everything we thought we knew about the space above and below our galaxy. Because these bubbles aren't just sitting there, they're evidence of something that happened long ago, something powerful and violent, an event so energetic that it left scars, reaching tens of thousands of light years into the space surrounding our galactic home. The discovery came from NASA's Fermi Gamma Ray Space Telescope, an instrument designed to see the universe in wavelengths far beyond what our eyes can perceive. For 2 years after its launch in 2008, it had been quietly mapping the sky, recording gamma-ray photons as they arrived from every direction. Most of these came from expected sources: pulsars spinning in the disk, distant active galaxies, the diffuse glow of cosmic rays colliding with interstellar gas. But as scientists began to analyze the data more carefully, they noticed something strange. There was too much gamma-ray emission coming from above and below the galactic center. Not just a little too much, but far too much, forming 2 distinct lobes that stretched across huge portions of the sky. At first, they thought it might be an error, an artifact of the data processing, a ghost in the machine. But the more they looked, the clearer it became. The emission was real. It had structure, it had edges, and it had symmetry. Above the galactic plane, a vast bubble of gamma rays extended upward. Below it, another bubble extended downward. Each one spanned roughly 25,000 light-years from the galactic center to its outer edge, making the combined structure about 50,000 light-years from top to bottom. To put that in perspective, that's half the diameter of the entire Milky Way's visible disk. These weren't small features. They were among the largest structures associated with our galaxy, and they'd been invisible until the right instrument came along. The light from these bubbles comes from something called inverse Compton scattering. Electrons moving at nearly the speed of light collide with lower energy photons, transferring some of their energy and boosting those photons into the gamma-ray range. For this to happen, there must be enormous populations of high-energy electrons filling these regions. Electrons that were accelerated by some powerful process. The bubbles glow because they're full of energetic particles, like embers still radiating heat long after the fire has died down. Whatever created them released enough energy to accelerate electrons across a volume measuring tens of thousands of light years. The scale of that event defies easy comprehension. The edges of the bubbles are sharp, unusually so. In space, most structures are diffuse and gradual, their boundaries soft and blurred. But the Fermi bubbles, as they came to be called, have relatively well-defined edges, as if something carved them out of the surrounding space. This sharpness suggests that they're still actively maintained by some ongoing process, or that they were created relatively recently in cosmic terms. If they'd been around for billions of years, they would have dispersed and blended into the background. But they haven't. They remain distinct, hovering above and below the galactic center, like twin monuments to a forgotten cataclysm. What could create something like this? That question opened one of the most intriguing mysteries in modern astrophysics. The energy required to inflate these bubbles is staggering. Some estimates suggest it would take the equivalent of 100,000 supernovae, all exploding in a relatively short period of time, to create such a structure. Alternatively, it could have been caused by the supermassive black hole at the center of the Milky Way, the object we call Sagittarius A star. Black holes don't just pull matter in. Under the right conditions, they can also eject it, blowing powerful jets and winds into space. If Sagittarius A star went through an active phase millions of years ago, feeding on gas and stars that ventured too close, it could have released enough energy to carve out these bubbles. Either way, the Fermi bubbles are evidence that something dramatic happened in the relatively recent past. Something that reshaped the space above and below our galaxy. The discovery also revealed something profound about the nature of the Milky Way itself. For a long time, we thought of our galaxy as a relatively quiet place, at least compared to more violent systems like active galaxies or quasars. We live in what astronomers call a normal spiral galaxy, orderly and calm. But the Fermi bubbles suggest otherwise. They suggest that even here, in our own galactic neighborhood, there have been episodes of extraordinary violence. The galaxy we call home has a history, a past filled with events powerful enough to send shock waves echoing through space for tens of thousands of light years. And these bubbles aren't the only structures that exist above and below the galactic disk. They're just the most dramatic, the easiest to see once you have the right tools. But they're part of a much larger story, a story about the vertical dimension of the Milky Way, the regions that extend perpendicular to the flat spiral we're so familiar with. Most of the time, when we think about the galaxy, we think horizontally. We imagine the spiral arms stretching outward in a plane. We picture the disk as a flat structure spinning through space. But the Milky Way is not flat. It has depth. It has height. And in those vertical directions, above and below the bright concentration of stars we call the disk, there are layers and structures just as important as anything in the plane itself. The space above and below the disk is not empty. It's filled with old stars, globular clusters, streams of gas, and as the Fermi bubbles show, the remnants of powerful outflows from the galactic center. It's a region where the galaxy breathes, where matter and energy are exchanged between the dense disk and the diffuse halo beyond. It's a transition zone, a boundary between the familiar and the mysterious, and for most of history, we barely knew it existed. So tonight, we're going to travel there. We're going to explore the vertical dimension of the Milky Way, the structures that rise above and fall below the plane of the disk. We're going to see what lies in those directions, what they tell us about the galaxy's past, and why understanding them changes the way we think about our cosmic home. The Fermi bubbles are just the beginning, the most obvious sign that there's far more to our galaxy than the flat spiral we see stretched across the night sky. Above and below, there are mysteries waiting, structures that challenge our understanding, and a history written in light we can barely perceive. To understand what lies above and below the Milky Way, it helps to first understand where we are. We live inside the disk, not at its center, not at its edge, but somewhere comfortably in between, about 27,000 light-years from the galactic core. Our solar system sits within one of the spiral arms, a region of space where stars are more densely packed than in the spaces between the arms. This arm is called the Orion arm, sometimes referred to as the Orion spur, a relatively minor branch compared to the galaxy's major structures like the Perseus or Sagittarius arms. It's a quiet neighborhood, cosmically speaking, without too many massive stars or violent supernova events nearby. The Sun orbits the center of the galaxy at a speed of about 200 kilometers per second, completing one full revolution every 230 million years or so. That's a long time. It means that since the Sun formed about 4.5 billion years ago, it has circled the galaxy roughly 20 times. The disk of the Milky Way is where most of the galaxy's visible matter resides. It's a relatively thin structure, about 1,000 light-years thick at our location, though it thickens somewhat toward the center and thins toward the edges. Compared to its width, about 100,000 light-years across, the disk is incredibly flat, like a sheet of paper compared to its length. This flatness is a consequence of rotation. As the galaxy formed billions of years ago, the conservation of angular momentum caused the gas and stars to settle into a plane, flattening over time into the structure we see today. Within this disk, stars orbit in relatively orderly paths, all moving in roughly the same direction around the galactic center. It's this organized motion that gives the Milky Way its spiral structure, those graceful arms winding outward from the core. From our vantage point inside the disk, we see the rest of the galaxy as a band of light stretching across the night sky. This is the view we've known for all of human history. The Milky Way as a river of stars arcing overhead. Ancient cultures around the world saw it and wove it into their myths and cosmologies. Some called it a path of souls. Others saw it as a bridge between worlds. The Greeks called it galaxias kyklos, the Milky Circle, which is where our modern word galaxy comes from, but none of them could have known what it really was. A cross-section view of an enormous disk of stars seen from the inside. When we look toward the constellation Sagittarius, we're looking toward the galactic center, where the disk is thickest and the stars are most concentrated. When we look in the opposite direction, toward Auriga and Taurus, we're looking toward the outer edge of the galaxy, where the density of stars drops off. The disk is not just made of stars, it's filled with gas and dust, the raw materials for future star formation. These clouds of molecular hydrogen, often mixed with heavier elements and tiny grains of dust, gather along the spiral arms where density waves compress them. Over time, gravity pulls these clouds together until they collapse, igniting new stars. Some of the youngest stars in the galaxy, hot blue giants that burn fiercely and die young, are found in these star-forming regions within the disk. Others, like our Sun, are older, middle-aged stars that formed long ago and have settled into more stable orbits. The disk is also home to the galaxy's magnetic field, a vast network of invisible lines of force that thread through the gas and dust. This field plays a role in shaping the structure of the spiral arms and in guiding the motion of charged particles, cosmic rays that stream through space at nearly the speed of light. The magnetic field, though weak by terrestrial standards, extends across enormous distances and helps to regulate the flow of matter through the disk. It's part of the reason why the Milky Way isn't a chaotic tangle of stars, but instead has the organized, layered structure we observe. Living in the disk means that our view of the universe is shaped by our location. When we look up or down, perpendicular to the plane of the galaxy, we see far fewer stars. The sky in those directions is darker, more transparent. This is because we're looking out through the thin dimension of the disk, through only 1,000 light-years of material, rather than across its width. This difference in density has profound consequences for astronomy. It means that when we observe distant galaxies, we preferentially look in directions above and below the galactic plane, where the view is less obstructed by our own galaxy's gas and dust. The regions near the plane, often called the zone of avoidance, are harder to study because so much intervening material blocks our view. But this also means that for most of history, we paid less attention to what lies directly above and below us. Our focus was on the disk itself, on the bright band of the Milky Way stretching across the sky. The regions perpendicular to the disk seemed empty by comparison, dark voids with only a scattering of faint stars. It wasn't until the 20th century that astronomers began to realize how much we were missing. The space above and below the disk isn't empty. It's part of a much larger structure, a spherical halo that surrounds the disk and extends far beyond its edges. The stars in the disk follow predictable, circular orbits. Their motion is tied to the overall rotation of the galaxy, and their paths are confined mostly to the plane. But if you look closely, you'll notice that not all stars behave this way. Some have orbits that take them far above and below the disk, plunging through the plane and then arcing back out again in long ellipses. These stars don't belong to the disk in the same way the Sun does. They're part of the halo, the diffuse population of stars that surrounds the galaxy like an invisible cloud. The halo stars are different from the stars in the disk in several important ways. They're older, for one thing. Many of them formed in the early universe, more than 10 billion years ago, when the galaxy was still young and taking shape. Their chemical compositions reflect this age. They contain far fewer heavy elements than the Sun does, because they formed before multiple generations of stars had lived and died, seeding space with the products of nuclear fusion. These old stars are also moving differently. Instead of following the orderly rotation of the disk, they move in random, chaotic orbits. Some travel in one direction, some in another. Some have orbits tilted at steep angles to the plane. Their motion preserves the memory of the galaxy's violent early history, a time when smaller systems merged and collided, scattering stars in every direction. The halo is where the galaxy begins to blur into the larger universe. It's a transition region, a place where the density of stars drops dramatically, but where the galaxy's gravitational influence still dominates. The halo extends far beyond the disk, reaching out to distances of several 100,000 light-years. Within it, you'll find not just individual stars, but also globular clusters, dense spheres of hundreds of thousands of stars bound tightly together by gravity. These clusters orbit the galactic center in long, looping paths, most of them spending their time well above or below disk. From within the disk, we can see some of these globular clusters scattered across the sky. They appear as fuzzy balls of light, too compact to resolve into individual stars with the naked eye, but beautiful through a telescope. Each one is an ancient relic, a survivor from the galaxy's early days. They're among the oldest objects we know, with ages rivaling the universe itself. Studying them helps astronomers understand the conditions that existed when the Milky Way was forming more than 12 billion years ago. The disk, for all its brightness and activity, is just one component of a much larger system. It's the most visible part, the part we experience directly, but it's not the whole story. Above and below, extending in directions we can't easily see from our flat vantage point, the galaxy continues. It spreads outward into a vast halo of old stars, dark matter, and diffuse gas. And within that halo, as we're now discovering, there are structures just as dramatic as anything in the disk itself. Structures like the Fermi bubbles, which tower above and below the plane like monuments to a forgotten past. So, when we talk about what lies above and below the galaxy, we're not talking about empty space or a void beyond the stars. We're talking about a region that's integral to the galaxy's structure and history. The disk may be where the action is, where stars are born and where the spiral arms shine brightest. But the halo, the vertical dimension, is where the galaxy keeps its memories. It's where the ancient past is preserved in the orbits of old stars and in the faint structures that float in the darkness. Understanding the disk is just the beginning. To truly understand the Milky Way, we have to look up and down, beyond the plane, into the hidden dimensions that surround us. The realization that the Milky Way extended vertically, that it had structure beyond the flat disk, came gradually over the course of the early 20th century. Before that, astronomers barely understood that we lived inside a galaxy at all. For much of the 19th century, the prevailing view was that the Milky Way was the entire universe, a collection of stars bound together in a roughly disc-shaped cloud, with nothing beyond it but empty space. The faint, fuzzy patches visible through telescopes, objects called nebulae, were thought to be clouds of gas within our own system. The idea that some of them might be separate galaxies, island universes far beyond the Milky Way, was still controversial. That began to change in the 1920s, when Edwin Hubble used the newly constructed 100-inch telescope at Mount Wilson Observatory to observe the Andromeda Nebula in unprecedented detail. He was able to resolve individual stars within it, and, crucially, he identified a type of variable star called a Cepheid, whose brightness oscillates in a predictable way. By measuring the period of that oscillation, He could calculate the star's true luminosity, and from that, its distance. The result was shocking. Andromeda was far too distant to be part of the Milky Way. It was a separate galaxy, millions of light years away. This discovery expanded the known universe overnight. If Andromeda was a galaxy, then so were many other nebulae. The Milky Way was not alone. It was one galaxy among countless others, each one a vast collection of stars stretching across enormous distances. But even as the scale of the universe expanded outward, astronomers began to refine their understanding of the Milky Way itself. If our galaxy was just one among many, what shape did it have? How big was it? And most importantly, where were we within it? One of the key figures in answering these questions was Harlow Shapley, who studied globular clusters, those dense spheres of ancient stars scattered around the galaxy. Shapley noticed that the globular clusters were not distributed evenly across the sky. Instead, most of them were concentrated in one direction, toward the constellation Sagittarius. This asymmetry suggested that we were not at the center of the galaxy's distribution of matter. The center was somewhere else, in the direction where the globular clusters were most densely packed. By measuring the distances to these clusters, Shapley was able to estimate the size of the Milky Way and our position within it. His results showed that the galaxy was far larger than anyone had thought, about 100,000 light-years across, and that the Sun was not at its center, but rather far out toward the edge. This was a profound shift in perspective, one that echoed Copernicus's earlier realization that Earth was not the center of the solar system. We were not at the center of the galaxy either. We were just one more star in a vast structure, located in an unremarkable part of the disk. But Shapley's work revealed something else, something equally important. The globular clusters were not confined to the plane of the Milky Way. They orbited above and below the disk, moving in long looping paths that carried them far from the flat structure most astronomers were focused on. This meant that the galaxy had a vertical dimension, a spherical component that extended well beyond the bright band of stars we saw as the Milky Way. The disk was just one part of a larger system. Surrounding it, in all directions, was a halo of ancient stars and clusters. This was the first clear evidence that the Milky Way was not simply a flat disk, but a three-dimensional structure with depth. The halo was diffuse, far less dense than the disk, but it was real. It contained billions of stars, most of them old and faint, moving in orbits that took them far from the galactic plane. Some of these stars had been part of the galaxy since its formation. Others, as we would later discover, had been captured from smaller galaxies that merged with the Milky Way over billions of years. The halo was a record of the galaxy's history, a fossil layer preserving the memory of its assembly. Understanding the halo required new tools and new ways of thinking. Most of astronomy up to that point had focused on objects within the disk, the bright stars and nebulae that were easiest to see. The halo stars were faint and scattered, hard to study individually, but by looking at their collective properties, by measuring their positions, motions, and chemical compositions, astronomers could begin to piece together the larger picture. The halo wasn't just a random collection of stars. It had structure, it had layers, and it contained clues to the galaxy's past. One of the key discoveries was that halo stars are metal poor, meaning they contain far fewer heavy elements than the Sun or other disk stars. In astronomical terminology, metals are any elements heavier than hydrogen and helium, and their abundance tells you when and where a star formed. Stars that formed early in the universe's history, before many generations of stars had lived and died, have very low metal content because the raw materials for making heavy elements didn't exist yet. The fact that halo stars are metal poor means they're ancient, formed in the first billion years after the Big Bang. They're among the oldest stars in the galaxy, relics from a time when the Milky Way was still taking shape. As astronomers mapped more and more halo stars, they noticed something else. The stars weren't moving randomly. Their orbits showed patterns, subtle but unmistakable. Some stars moved together in groups, following similar paths through space. These groups, called stellar streams, were the remnants of smaller galaxies that had been torn apart by the Milky Way's gravity. As these smaller systems fell into the gravitational well of our galaxy, tidal forces stretched them, pulling stars away from their cores and leaving behind long trails that orbited the Milky Way, like the remnants of a comet's tail. These streams were evidence that the Milky Way had grown over time by consuming its neighbours, absorbing their stars into its halo. The discovery of the halo and the realization that it extended far above and below the disk changed the way astronomers thought about galaxies in general. It meant that the bright disk was just the tip of the iceberg, the visible part of a much larger structure. Most of the galaxy's volume was occupied by the halo, even though most of its stars were in the disk. And within that halo, there were layers of complexity, regions with different densities, different ages, different chemical compositions. The vertical dimension of the galaxy was not an afterthought. It was essential to understanding how the Milky Way formed and evolved. But even as the halo came into focus, there were hints of something more, something even harder to detect. When astronomers measured the motions of stars in the outer parts of the galaxy, they found that the stars were moving faster than they should be. According to Newton's laws, the farther a star is from the galactic center, the slower it should orbit, just as planets farther from the sun move more slowly. But the observations didn't match the predictions. The stars weren't slowing down as much as they should. This suggested that there was more mass present than could be accounted for by the visible stars and gas. There was something else out there, something invisible, holding the galaxy together. This invisible mass, whatever it was, had to be distributed throughout the galaxy, including in the halo above and below the disk. It became known as dark matter, and its discovery opened an entirely new chapter in our understanding of the Milky Way's structure. The halo wasn't just made of old stars and globular clusters. It was also filled with dark matter, an unseen substance that made up most of the galaxy's mass. This dark matter halo extended far beyond the visible stars, reaching out to distances of hundreds of thousands of light years, shaping the galaxy's gravitational field and determining how stars and gas moved within it. The vertical dimension of the Milky Way, once thought to be mostly empty, was now revealed to be full of invisible structure. Dark matter dominated the halo, forming a vast spherical envelope around the disk, and within that envelope, the old stars and globular clusters traced out the galaxy's history, their orbits shaped by the combined gravity of the visible and invisible matter. Looking up and down from the disk, we weren't looking into emptiness. We were looking into a hidden realm, a three-dimensional structure that surrounded us on all sides. This discovery fundamentally changed astronomy. It meant that the flat view of the galaxy we'd been studying for so long was incomplete. The disk was important, but it was embedded within something much larger. The halo, with its ancient stars, its dark matter, and its complex history, was just as essential to understanding the Milky Way. And as we developed better tools, better telescopes, better ways of detecting faint light and invisible matter, we would discover even more. The space above and below the disk wasn't just a graveyard for old stars. It was alive with structure, with energy, with mysteries that would take decades to unravel. Once astronomers realized that the Milky Way had a vertical dimension, that the galaxy extended far above and below the familiar disk, the challenge became how to map it. This was not a simple task. Observing the halo was fundamentally different from observing the disk. The disk was bright, filled with young stars, glowing nebulae, and dense clouds of gas. The halo, by contrast, was dim and sparse, populated mostly by old faint stars scattered across enormous volumes of space. These stars were hard to see individually, and even harder to study in detail. And then there was the dark matter, the invisible substance that made up most of the halo's mass but emitted no light at all. How do you map something you can't see? The early efforts focused on what could be observed: the globular clusters and the brightest halo stars. Harlow Shapley had already shown that globular clusters could be used to trace the galaxy's structure, and in the decades following his work, astronomers expanded on this approach. They catalogued more clusters, measured their distances more precisely, and tracked their motions through space. Each cluster orbited the galactic center in a long elliptical path, and by studying these orbits, astronomers could infer the distribution of mass within the galaxy. The clusters moved under the influence of gravity, and their trajectories revealed where the gravitational pull was strongest. What they found was surprising. The orbits of the globular clusters suggested that the galaxy's mass was not concentrated in the disk, where most of the visible stars were, but was instead distributed throughout a much larger volume. The halo had to contain far more mass than the stars within it could account for. This was one of the earliest pieces of evidence for dark matter, though it would be decades before astronomers fully understood what that meant. For now, the focus was on mapping the visible components, the stars and clusters that could actually be observed. Photographing the halo stars required patience and precision. Unlike the bright stars of the disk, which could be captured in short exposures, the faint stars of the halo required long integration times, sometimes hours, to gather enough light. Early photographic plates were not very sensitive, and the process of identifying halo stars among the much more numerous foreground stars of the disk was tedious. Astronomers had to carefully measure the positions, brightnesses, and colors of thousands of individual stars, then use statistical methods to separate the halo population from the disk population. It was slow work, but gradually a picture began to emerge. The halo stars were not distributed evenly. They were denser near the galactic center and thinned out with increasing distance. This was expected. Gravity naturally causes matter to concentrate toward the center of a system. But there were also asymmetries, regions where the density was slightly higher or lower than average. These variations hinted at structure within the halo, perhaps the remnants of past mergers or the effects of the galaxy's rotation. Mapping these structures required observations across the entire sky, a task that took decades and involved astronomers from around the world. One of the key breakthroughs came with the development of spectroscopy, the technique of splitting light into its component wavelengths to study its properties. By analyzing the spectra of halo stars, astronomers could determine their chemical compositions, their temperatures, and most importantly, their motions. The Doppler shift, the change in wavelength caused by a star's motion toward or away from us, allowed astronomers to measure radial velocities with high precision. Combined with measurements of a star's position on the sky, this data could be used to reconstruct its three-dimensional motion through space, revealing the orbit it followed around the galaxy. These velocity measurements confirmed what the globular cluster orbits had suggested. The halo stars moved in chaotic, random directions, quite unlike the orderly rotation of the disk. Some stars moved in the same direction as the disk's rotation, others in the opposite direction, and many had orbits tilted at steep angles to the plane. This randomness was a signature of the halo's origin. The disk had formed from gas that settled into a rotating plane, but the halo had formed differently, through the merger and disruption of smaller systems whose stars retained the memory of their original motions. As more data accumulated, astronomers began to notice something else. Some groups of halo stars moved together, following similar orbits through space. These groups, later identified as stellar streams, were the remnants of globular clusters or small dwarf galaxies that had been torn apart by the Milky Way's gravity. As these objects fell into the galaxy, tidal forces stretched them, pulling stars away and spreading them along their orbital path. Over time, these stars formed long, thin streams that wrapped around the galaxy like threads. Mapping these streams provided direct evidence that the Milky Way was still growing, still absorbing smaller systems from its surroundings. But mapping the halo's structure was only part of the challenge. Understanding its vertical extent, how far it reached above and below the disk, required observations that could probe to great distances. One approach was to use RR Lyrae stars, a type of variable star commonly found in the halo. These stars pulsate regularly, changing brightness in a predictable way, and their intrinsic luminosity is well understood. By measuring how bright an RR Lyrae star appears from Earth, astronomers could calculate its distance, even if it was tens of thousands of light-years away. These stars became cosmic distance markers, allowing astronomers to trace the halo's structure in 3 dimensions. The results showed that the halo extended far beyond the disk. While the disk was only about 1,000 light-years thick, the halo reached out to distances of 200,000 light-years or more, forming a vast spherical envelope around the galaxy. Within this envelope, the density of stars decreased steadily with distance, but there was no sharp boundary, no clear edge where the halo ended. Instead, it faded gradually into the intergalactic medium, blending into the space between galaxies. The Milky Way, it turned out, was much larger than the bright disk suggested. Most of its volume was occupied by the halo, even though most of its stars were in the disk. Mapping the dark matter halo was even more difficult. Since dark matter doesn't emit or absorb light, it can only be detected through its gravitational effects. Astronomers used the motions of stars and gas clouds to infer where the dark matter was and how much of it there was. By measuring how fast stars orbited at different distances from the galactic center, they could construct a rotation curve, a graph showing orbital speed versus distance. In a system dominated by visible matter, the rotation curve should drop off with distance, following Kepler's laws. But the Milky Way's rotation curve stayed flat, indicating that there was a large amount of unseen mass extending far beyond the visible stars. This unseen mass had to be distributed throughout the halo, forming a dark matter halo that extended even farther than the stellar halo. Computer simulations suggested that this dark matter halo could reach out to nearly 1 million light-years, halfway to the Andromeda galaxy. It was this dark matter that provided most of the galaxy's gravitational pull, holding the disk together and shaping the orbits of everything from individual stars to satellite galaxies. The halo, both visible and invisible, was the skeleton of the Milky Way, the framework that gave the galaxy its shape and structure. As mapping efforts continued, new technologies brought new insights. Radio telescopes, which detect light at much longer wavelengths than visible light, could see through the dust and gas that obscured parts of the disk and halo. They revealed clouds of neutral hydrogen gas extending far above and below the plane, part of the galaxy's extended atmosphere. Infrared telescopes, sensitive to heat rather than visible light, could detect cool stars and dust clouds that were invisible to optical telescopes. X-ray telescopes, which observed the highest energy photons, revealed hot gas filling parts of the halo, heated by supernova explosions and outflows from the galactic center. Each new wavelength added a new layer to the map, revealing structures that had been hidden before. The halo was not a simple, empty void. It was filled with gas, dust, stars, and dark matter, all organized in complex ways. There were shells and streams, bubbles and filaments, regions of high density and regions of near emptiness. And towering above and below the galactic center, though not yet discovered, were the Fermi bubbles, waiting for the right instrument to reveal them. The first response to the discovery of the halo, then, was one of careful, methodical observation. Astronomers had to develop new techniques, new instruments, and new ways of thinking to map a structure that was mostly invisible. It was slow work, but it was essential. Understanding the halo meant understanding the galaxy as a whole, seeing it not as a flat disk but as a three-dimensional system with depth, with history, with layers upon layers of complexity. The Milky Way extended far above and below the plane, and mapping that vertical dimension would occupy astronomers for generations to come. By the middle of the 20th century, astronomers had mapped enough of the Milky Way's halo to understand its basic structure. They knew it was spherical, extending far above and below the disk. They knew it contained ancient stars and globular clusters, relics from the galaxy's early history. They knew these objects moved in chaotic orbits, quite unlike the orderly rotation of the disk, and they had measured distances and velocities with increasing precision, building a three-dimensional picture of the galaxy's shape. But the more they learned, the more something seemed wrong. The numbers didn't add up. There was a fundamental contradiction at the heart of their observations, one that would eventually lead to one of the most profound discoveries in modern astronomy. The problem was mass. When astronomers calculated how much mass the Milky Way should contain based on the stars they could see, the gas they could measure, and the dust they could detect, they got one number. But when they calculated how much mass the galaxy needed to hold itself together, to keep the stars orbiting at the speeds they observed, they got a much larger number. The difference was enormous. The visible matter, everything that emitted or absorbed light, accounted for only a small fraction of the total mass required. The rest was missing. This became apparent through careful measurements of rotation curves, graphs showing how fast stars and gas clouds orbit the galaxy at different distances from the center. According to Newton's laws of gravity, the orbital speed should decrease with distance, following a predictable pattern. Close to the center, where most of the mass is concentrated, the gravitational pull is strong and stars orbit quickly. Farther out, where there's less mass, the pull is weaker and stars should orbit more slowly. This is exactly what we see in the solar system. Mercury, closest to the Sun, orbits at 48 kilometers per second, while Neptune, far from the Sun, orbits at only 5 kilometers per second. But when astronomers measured the Milky Way's rotation curve, they found something unexpected. Instead of dropping off with distance, the orbital speeds stayed roughly constant, even in the outer parts of the galaxy where there were very few visible stars. Stars and gas clouds 50,000 light-years from the center were moving just as fast as those at 25,000 light-years. This flat rotation curve was a puzzle. If the only mass present was the mass we could see, the stars in the outer regions should be moving much more slowly. The fact that they weren't meant there had to be additional mass out there, mass that we couldn't detect directly. The Dutch astronomer Jan Oort was one of the first to notice this problem. In the 1930s, he studied the motions of stars near the Sun and calculated how much mass was needed to account for their velocities. There seemed to be more gravitational influence than the visible stars could explain. At the time, he attributed this to faint stars and interstellar matter that was hard to detect. But as observational techniques improved and the discrepancy persisted, it became clear that the missing mass couldn't be explained by ordinary matter that was simply too dim to see. The problem became even more apparent when astronomers extended their measurements to the outer halo. By tracking the motions of globular clusters and satellite galaxies orbiting the Milky Way at distances of 100,000 light-years or more, they could probe the galaxy's gravitational field at its extremes. These distant objects were moving too fast. Their orbital speeds indicated that the Milky Way's gravity extended far beyond the visible disk and halo, out to distances where almost no stars could be detected. There had to be a massive dark halo surrounding the entire galaxy, something that contributed to the gravitational field but didn't emit any light. Similar observations were being made in other galaxies. In the 1970s, astronomer Vera Rubin and her colleagues studied the rotation curves of spiral galaxies similar to the Milky Way. Using spectroscopy, they measured the velocities of gas clouds in the outer regions of these galaxies, where very few stars were visible. They found the same flat rotation curves. The gas was moving too fast, implying the presence of far more mass than could be accounted for by stars, gas, and dust. This was not a problem unique to the Milky Way. It was universal. Every spiral galaxy they studied showed the same pattern. The contradiction was unavoidable. Either our understanding of gravity was wrong, or there was a vast amount of matter in the universe that we couldn't see. For a while, some scientists explored the first possibility. Perhaps Newton's and Einstein's laws of gravity needed to be modified at galactic scales. Various alternative theories were proposed, attempting to explain the flat rotation curves without invoking invisible matter. But these theories struggled to explain other observations, and they required assumptions that seemed arbitrary or contrived. The simplest explanation, though it sounded almost absurd, was that most of the universe's matter was dark. This dark matter, whatever it was, had to have certain properties. It had to interact gravitationally, pulling on stars and gas and shaping the structure of galaxies. But it couldn't interact electromagnetically, meaning it didn't emit, absorb, or reflect light. It was invisible to all forms of electromagnetic radiation, from radio waves to gamma rays. It passed through ordinary matter without leaving a trace, except for its gravitational pull. And there had to be a lot of it, at least 5 times as much as all the ordinary matter in the universe combined. The realization that the Milky Way's halo was dominated by dark matter changed everything. The halo wasn't just a sparse collection of old stars orbiting in the space above and below the disk. It was a vast, massive structure made mostly of invisible particles. The stars and globular clusters were just tracers, visible markers of a much larger dark matter halo that extended hundreds of thousands of light years in all directions. This dark matter halo provided the gravitational framework that held the galaxy together. Without it, the disk would fly apart, its stars flung into intergalactic space by their own orbital velocities. Understanding the distribution of dark matter in the halo became a major goal of astronomy. Since it couldn't be seen directly, its presence had to be inferred from its effects. Astronomers used computer simulations to model how dark matter should be distributed if it formed under the influence of gravity alone. These simulations started with the early universe, just after the Big Bang, when matter was distributed almost uniformly. Tiny fluctuations in density, seeded by quantum variations during cosmic inflation, grew over time. Dark matter, unaffected by radiation pressure or electromagnetic forces, could clump together more easily than ordinary matter. It formed the first structures, creating gravitational wells into which ordinary matter later fell. The simulations showed that dark matter should form roughly spherical halos around galaxies, denser near the center and gradually thinning with distance. The exact shape depended on how the galaxy formed, on its merger history and rotation, but in general, the dark matter halo should extend far beyond the visible galaxy, creating a smooth gravitational potential that shaped the motion of everything within it. The Milky Way's flat rotation curve fit this picture perfectly. The dark matter halo provided exactly the right amount of mass at the right distances to keep stars and gas orbiting at constant speeds. But what was dark matter made of? That question remained unanswered. It couldn't be ordinary atoms, protons and neutrons and electrons, because we could account for most of the ordinary matter in the universe through other observations. Measurements of the cosmic microwave background, the afterglow of the Big Bang, showed how much ordinary matter existed in the early universe, and that amount matched what we saw in stars, gas, and dust. The dark matter had to be something else, some new type of particle that hadn't been discovered yet. One possibility was that dark matter consisted of weakly interacting massive particles, or WIMPs, hypothetical particles that had mass but interacted only through gravity and the weak nuclear force. These particles would have been created in the Big Bang in enormous numbers, and they would still be passing through space today, invisible and undetectable except through their gravitational effects. Another possibility was axions, ultralight particles that could exist in vast quantities, forming a kind of diffuse field permeating space. Or perhaps dark matter was made of primordial black holes, tiny black holes formed in the early universe, too small to emit much radiation but massive enough to contribute to the galaxy's gravity. Despite decades of searching, no one has definitively detected a dark matter particle. Experiments deep underground, shielded from cosmic rays, have been built to try to catch the rare collisions between dark matter particles and ordinary atoms. So far, they've found nothing conclusive. Dark matter remains as elusive as ever, known only through its gravitational influence. And yet that influence is undeniable. The contradiction between the mass we see and the mass we need cannot be explained away. Dark matter is real, even if we don't yet understand what it is. The realization that most of the galaxy's mass is invisible had profound implications for understanding the space above and below the disk. The halo was not a secondary feature, a sparse afterthought to the bright disk. It was the primary structure, the foundation on which everything else was built. The disk formed within the dark matter, halo, settling into a rotating plane as gas cooled and condensed. The stars we see, the spiral arms, the bright band of the Milky Way across the night sky, all of it exists because the dark matter halo provided the gravitational well that allowed matter to accumulate. When we look up or down from the disk, we're looking through the dark matter halo. It surrounds us on all sides, invisible but essential. Every star in the halo, every globular cluster, every stream of gas moves within this invisible ocean. The halo's structure, its extent, its distribution, all are determined by the dark matter. And as we would later discover, the halo is not static. It's dynamic, shaped by ongoing processes, by inflows and outflows of matter, by the activity of the galaxy itself. The space above and below the disk is alive with motion and energy, even if most of it is hidden from view. The contradiction between visible and total mass led astronomers to a humbling realization. Most of the universe is invisible. Everything we can see, the stars, planets, nebulae, galaxies, all of it makes up only a small fraction of what exists. The rest is dark matter and dark energy, mysterious substances that dominate the cosmos but remain poorly understood. The Milky Way is not primarily a disk of stars. It's primarily a halo of dark matter within which a disk of stars is formed. When we ask what lies above and below the galaxy, the answer begins with dark matter. It's the unseen architecture that defines the galaxy's shape and holds it together across billions of years. Once the contradiction became clear, once it was undeniable that most of the galaxy's mass was invisible, astronomers began developing theories to explain what they were seeing. The space above and below the disk, the vertical dimension of the Milky Way, became a laboratory for testing ideas about the nature of matter, gravity, and the formation of cosmic structures. Different camps emerged, each with their own interpretation of the observations. Some focused on the dark matter itself, trying to understand what it was made of and how it behaved. Others looked at the visible components, the stars and gas in the halo, searching for patterns that might reveal the galaxy's history. And a few explored alternative explanations, wondering if perhaps our understanding of gravity needed revision. The most widely accepted theory was that dark matter consisted of some new type of particle, something that had been predicted by certain extensions of the standard model of particle physics, but had never been detected. The leading candidate was the WIMP, the weakly interacting massive particle. These particles, if they existed, would have been produced in enormous numbers during the Big Bang. They would have mass, perhaps tens or hundreds of times the mass of a proton, but they would interact only through gravity and the weak nuclear force. This meant they would rarely collide with ordinary matter. They would pass through planets, stars, even our bodies, without leaving a trace. According to this theory, the Milky Way's halo was filled with a vast cloud of WIMPs, billions upon billions of them streaming through space in all directions. They moved under the influence of gravity, orbiting the galactic center in complex paths. Near the center, where the gravitational pull was strongest, the density of dark matter would be higher. Farther out, it would thin gradually, extending to distances far beyond the visible stars. This distribution created a smooth gravitational potential, a kind of invisible bowl within which the disk formed and rotated. The dark matter provided the scaffolding, the framework that allowed the galaxy to exist in the first place. Computer simulations supported this picture. When physicists modeled the formation of galaxies using only gravity and dark matter, they found that halos formed naturally, starting from a nearly uniform distribution of matter in the early universe. Gravity amplified tiny fluctuations, pulling matter into clumps. These clumps grew over time, merging with each other to form larger structures. The result was a cosmic web of dark matter filaments and halos, within which galaxies formed. The Milky Way's dark matter halo was just one node in this larger web, connected by invisible threads to the halos of neighboring galaxies. But dark matter was not the only mystery in the halo. There were also the visible structures, the stars and gas that traced out the halo's shape. These too required explanation. Why were halo stars so old? Why did they move in chaotic orbits? Why were there stellar streams wrapping around the galaxy? And what caused the chemical differences between halo stars and disk stars? To answer these questions, astronomers developed theories about how the Milky Way formed and evolved over billions of years. The prevailing theory was hierarchical assembly. According to this model, the Milky Way did not form all at once. Instead, it grew gradually through the merger of smaller systems. In the early universe, dark matter halos collapsed first, forming the gravitational wells into which ordinary matter fell. Within these halos, the first stars formed, creating small dwarf galaxies. Over time, these dwarfs collided and merged, building larger galaxies. The Milky Way was the product of countless such mergers, each one adding stars, gas, and dark matter to the growing system. The halo stars were the remnants of these ancient mergers. When a small galaxy fell into the Milky Way, tidal forces stretched it, pulling stars away from its center and scattering them throughout the halo. These stars retained the memory of their origin. They moved in orbits that reflected the path their parent galaxy had followed before it was destroyed, and their chemical compositions preserved the conditions under which they formed, often in environments quite different from the Milky Way's disk. The halo was a graveyard of galaxies, each one contributing a population of stars that now moved independently through space. The stellar streams observed in the halo supported this theory. Each stream was the remnant of a globular cluster or dwarf galaxy that had been torn apart. As the object orbited the Milky Way, gravity pulled stars away from its edges, spreading them along its orbital path. Over time, the object dissolved completely, leaving behind only a trail of stars following the same orbit. By mapping these streams, astronomers could reconstruct the orbits of the parent objects and, in some cases, identify which dwarf galaxy or cluster they came from. The streams were like fossils, preserving the history of the galaxy's growth. Globular clusters fit into this picture as well. These dense spheres of stars were among the oldest objects in the galaxy, formed in the first billion years after the Big Bang. Many of them likely formed in smaller galaxies that were later absorbed by the Milky Way. As the Milky Way grew, it captured these clusters, which now orbited in the halo, survivors of the violent process of galactic assembly. Their orbits carried them far above and below the disk, tracing the shape of the dark matter halo. By studying their motions, astronomers could infer the distribution of mass in the galaxy, including the invisible dark matter. But not all theories focused on dark matter and mergers. A small group of scientists explored the possibility that the observations could be explained by modifying our understanding of gravity. The most prominent alternative was modified Newtonian dynamics, or MOND. This theory proposed that Newton's laws of gravity broke down at very low accelerations, the kind experienced by stars in the outer parts of galaxies. In this regime, the gravitational force would decrease more slowly than Newton predicted, allowing stars to orbit faster without requiring additional mass. If MOND were correct, there would be no need for dark matter. The flat rotation curves could be explained by a modification of gravity itself. MOND had some successes. It could reproduce the rotation curves of spiral galaxies with remarkable accuracy, often better than dark matter models. But it struggled to explain other observations, particularly those involving galaxy clusters and the cosmic microwave background. And it required introducing a new fundamental constant, a scale at which gravity's behavior changed without any theoretical justification for why such a scale should exist. Most astronomers remained skeptical. The evidence for dark matter from multiple independent sources, observations of galaxy clusters, gravitational lensing, the cosmic microwave background, was too strong to dismiss. Still, the debate highlighted an important point. The space above and below the disk, the halo, was not just a passive backdrop. It was a testing ground for fundamental physics. Every measurement of stellar motions, every observation of gas clouds, every detection of gravitational effects contributed to our understanding of how the universe worked. The halo was a natural laboratory, a place where theories could be tested against reality. Another set of theories focused on the gas in the halo. Observations showed that the space above and below the disk wasn't empty. It contained diffuse clouds of hydrogen and heavier elements, some of it cold and neutral, some of it hot and ionized. This gas was part of the galaxy's extended atmosphere, a region where matter cycled between the disk and the surrounding space. Theories about this gas had to explain where it came from, how it moved, and what role it played in the galaxy's evolution. One source of halo gas was supernova explosions. When massive stars died, they released enormous amounts of energy, blowing shells of gas outward at thousands of kilometers per second. Some of this gas escaped the disk entirely, rising into the halo where it cooled and eventually fell back down. This created a galactic fountain, a circulation of matter between the disk and the halo. The gas that fell back brought fresh material for star formation, while the outflows carried away heavy elements created in the supernova, enriching the halo with metals. Another source was gas falling into the galaxy from the intergalactic medium. The Milky Way is not a closed system. It constantly exchanges matter with its surroundings. Cold streams of gas flow inward along the filaments of the cosmic web, feeding the disk and sustaining star formation. These streams had to pass through the halo, and as they did, they interacted with the gas already there, mixing and heating. The halo was a transition zone, a boundary region where infalling material met the galaxy's own outflows. The hot gas in the halo, detected through X-ray observations, required a different explanation. This gas had temperatures of millions of degrees, far too hot to have come from ordinary stars or even supernova. It was likely heated by shock waves, either from the collective effect of many supernova or from activity at the galactic center. The Fermi bubbles, though not yet discovered at the time these theories were being developed, would later provide dramatic evidence of such heating. But even before their discovery, astronomers suspected that energetic processes at the galactic center could send shocks propagating through the halo, heating the gas and driving it outward. All of these theories, dark matter halos, hierarchical assembly, modified gravity, galactic fountains, shared a common theme. They tried to make sense of the invisible, to infer the nature of structures that couldn't be seen directly. The space above and below the disk was dominated by things we couldn't observe easily. Dark matter, faint old stars, diffuse gas. Understanding this region required combining observations from multiple wavelengths, from radio to gamma rays, and using theoretical models to interpret what those observations meant. The beauty of science is that theories can be tested. As new instruments came online, as telescopes became more sensitive and surveys mapped more of the sky, the predictions of different theories could be compared against reality. Some theories would be confirmed, others would be refined or discarded. The process was slow, but it was steady. Each new piece of data added to the picture, filling in gaps, resolving contradictions, revealing new layers of complexity. The halo was no longer a mystery to be feared or ignored. It was a puzzle to be solved, piece by piece, observation by observation. Understanding the space above and below the Milky Way required more than ground-based telescopes pointing at faint stars. It required a revolution in observational astronomy. New instruments that could see beyond the narrow band of visible light, that could detect wavelengths absorbed by Earth's atmosphere or drowned out by the sun's glare. It required satellites launched into orbit, telescopes floating above the atmosphere where they could observe the universe in X-rays, ultraviolet, infrared, and gamma rays. Each new wavelength revealed a different aspect of the halo, structures and processes that had been invisible before. The investigation of the vertical dimension became, in many ways, a story of technological innovation. One of the first breakthroughs came from X-ray astronomy. In the 1960s, rockets carrying X-ray detectors were launched on brief flights above the atmosphere, capturing a few minutes of data before falling back to Earth. These early missions discovered that the sky was not dark in X-rays. There were sources of high-energy radiation scattered across the heavens, including emission from the direction of the galactic center. But it wasn't until the launch of dedicated X-ray satellites that astronomers could study these sources in detail. The Rosat satellite, launched in 1990, was one of the most important early X-ray missions. It conducted an all-sky survey, mapping X-ray emission across the entire celestial sphere. Among its discoveries was a diffuse glow of X-rays filling much of the sky, particularly in directions perpendicular to the galactic plane. This emission came from hot gas in the halo, gas heated to millions of degrees by supernova shockwaves and other energetic processes. The X-ray observations showed that the space above and below the disk was not empty, but filled with a thin, hot atmosphere extending tens of thousands of light years from the plane. This hot gas was invisible to optical telescopes. At such high temperatures, it emitted most of its light at X-ray wavelengths, far beyond what the human eye could see. The discovery changed how astronomers thought about the halo. It wasn't just a collection of old stars and dark matter. It was also a dynamic environment where gas flowed, heated, and cooled, participating in the galaxy's ongoing evolution. The X-ray observations provided the first direct evidence that the Milky Way breathed, cycling matter between the disk and the halo. Infrared astronomy provided another critical perspective. Infrared light, with wavelengths longer than visible light, can penetrate dust clouds that block optical observations. This makes it ideal for studying the galactic disk, where thick clouds of dust obscure much of the starlight. But infrared observations also revealed structures in the halo that were hard to see at other wavelengths. Cool stars, those with surface temperatures of only a few thousand degrees, emit most of their light in the infrared. Many of the faintest halo stars, too dim to be easily detected in visible light, became visible in infrared surveys. NASA's WISE satellite, launched in 2009, conducted an all-sky infrared survey that catalogued hundreds of millions of stars. Among them were countless halo stars, including some of the oldest and most metal-poor stars known. By analysing the infrared colours and brightnesses of these stars, astronomers could estimate their distances and map their distribution in 3 dimensions. The survey revealed the structure of the halo in unprecedented detail, confirming the presence of stellar streams, shells, and other substructures left behind by ancient mergers. But perhaps the most transformative technology was radio astronomy. Radio telescopes, which detect light at wavelengths of centimeters to meters, can observe through clouds, through the atmosphere, even through the disk itself. They're sensitive to the emission from neutral hydrogen gas, the most abundant element in the universe. Hydrogen emits a characteristic signal at a wavelength of 21 centimeters, a line that can be detected across vast distances. By mapping this emission, astronomers could trace the distribution of gas in and around the galaxy. Radio surveys revealed that the Milky Way's gas did not end at the edge of the disk. There were vast clouds of hydrogen extending far above and below the plane, some of it forming coherent structures like arcs and filaments. One of the most dramatic discoveries was the Magellanic Stream, a ribbon of hydrogen gas trailing behind the Magellanic Clouds, the Milky Way's satellite galaxies. This stream extended over 200 degrees across the sky, wrapping around the galaxy like a ribbon. It showed that the interaction between the Milky Way and its companions was ongoing, with gas being stripped from the satellites and falling into the halo. Radio observations also detected high-velocity clouds, clumps of gas moving much faster than the general rotation of the disk. Some of these clouds were above the disk, others below, moving at hundreds of kilometers per second. Their origin was debated. Some might be gas expelled from the disk by supernova or stellar winds. now falling back under gravity. Others might be primordial gas, material that never formed stars, now being accreted onto the galaxy from the intergalactic medium. Either way, they showed that the halo was not static but filled with moving gas, part of the galaxy's ongoing cycle of matter. Ultraviolet astronomy added yet another layer. Ultraviolet light, with wavelengths shorter than visible light, is absorbed by Earth's atmosphere, so it can only be observed from space. The Hubble Space Telescope, equipped with ultraviolet spectrographs, allowed astronomers to study the gas in the halo by observing how it absorbed light from background sources. When light from a distant quasar passed through the Milky Way's halo on its way to Earth, it picked up absorption lines, dark features in the spectrum where atoms in the halo absorbed specific wavelengths. By analyzing these lines, astronomers could determine the composition, temperature, and velocity of the gas. These observations revealed that the halo contained multiple phases of gas with different temperatures and densities. There was cold neutral gas, warm ionized gas, and hot coronal gas, all coexisting in the same volume. The different phases formed a complex ecosystem, with gas constantly transitioning from one state to another, heated by shocks, cooled by radiation, mixed by turbulence. Understanding this ecosystem was crucial for understanding how galaxies evolve, because the flow of gas between the disk and the halo determined the rate at which new stars could form. The investigation of the vertical dimension also benefited from advances in optical astronomy. Large ground-based telescopes, equipped with wide-field cameras, conducted deep surveys of the sky, imaging millions of stars and galaxies. Projects like the Sloan Digital Sky Survey, which began in 2000, mapped a quarter of the sky in unprecedented detail. These surveys provided vast data sets that could be mined for information about halo structure. By selecting stars based on their colors and brightnesses, astronomers could identify halo stars and trace their distribution across the sky. One of the most important results from these surveys was the discovery of tidal streams in the halo. By plotting the positions of millions of stars and looking for patterns, astronomers found long, thin features stretching across large areas of the sky. These were the remnants of disrupted satellite galaxies and globular clusters. Their stars spread out along their former orbits. Each stream told a story of a past encounter, a small system that ventured too close to the Milky Way and was torn apart. Mapping these streams allowed astronomers to reconstruct the merger history of the galaxy, identifying which satellites had been absorbed and when. But the most dramatic discovery related to the vertical dimension came from gamma-ray astronomy. Gamma rays, the highest energy form of light, are produced by the most violent processes in the universe: black holes accreting matter, pulsars spinning at incredible speeds, cosmic rays colliding with gas. They're absorbed by Earth's atmosphere, so they can only be detected from space. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, was designed to survey the entire sky in gamma rays, building up a map over months and years of observation. The data from Fermi slowly accumulated. At first, astronomers saw the expected sources: pulsars in the disk, distant active galaxies, the diffuse glow of cosmic rays interacting with interstellar gas. But as they refined their analysis, subtracting known sources and smoothing the data to reveal faint large-scale structures, something unexpected emerged. There was excess gamma-ray emission above and below the galactic center, forming two distinct lobes that stretched across huge portions of the sky. These lobes were symmetric, mirror images of each other, reaching from the disk to distances of 25,000 light-years in both directions. At first, the team thought it might be an artifact, a glitch in the data processing. But as they checked and rechecked their work, the signal remained. It was real. The Milky Way had two enormous bubbles of gamma-ray emission towering above and below its centre. The discovery was announced in 2010, and it immediately became one of the most significant findings in galactic astronomy. The Fermi bubbles, as they were named, were proof that something extraordinary had happened in the galaxy's recent past, an event so energetic that it left scars visible across tens of thousands of light years. The investigation had revealed what no one had expected. The space above and below the disk was not a quiet, passive region. It was marked by the evidence of violence, of energy released on scales that dwarfed anything we see in the disk today. The bubbles glowed with gamma rays because they were filled with high-energy particles. Electrons accelerated to nearly the speed of light. Whatever created them, whether an outburst from the central black hole or a burst of supernova near the galactic center, it had reshaped the halo, carving out these enormous cavities and filling them with radiation. Each new instrument, each new wavelength, added a piece to the puzzle. X-rays showed hot gas, infrared revealed cool stars, radio mapped neutral hydrogen, ultraviolet probed ionized gas. Gamma rays exposed the bubbles. Together, these observations painted a picture of the vertical dimension as a complex, layered structure, filled with matter in different states, shaped by processes ranging from stellar evolution to black hole activity. The investigation was far from over, but the tools were now in place to explore the space above and below the galaxy in ways that would have been impossible just a few decades earlier. As the new instruments returned their data, as the surveys accumulated observations of millions of stars and vast clouds of gas, patterns began to emerge from the noise. The space above and below the Milky Way's disk was revealing its secrets, not all at once, but gradually, layer by layer. Each data set added detail, refining our picture of the halo's structure and composition. The challenge was integrating all this information, combining observations from different wavelengths and different instruments into a coherent whole. It required sophisticated analysis, careful modelling, and sometimes inspired guesswork. But slowly, the halo came into focus. One of the first things the data revealed was the extent of the halo. By measuring the distances to halo stars using techniques like RR-Lyrae variables and horizontal branch stars, astronomers could map how far the halo extended in all directions. The results showed that it reached at least 200,000 light-years from the galactic center, and possibly farther. This was much larger than the visible disk, which spanned only about 100,000 light-years. The halo was not a thin shell surrounding the disk, but a vast, roughly spherical structure within which the disk was embedded. The density of stars in the halo decreased with distance, following a smooth mathematical relationship. Close to the center, there were more stars per unit volume. Farther out, the density dropped off, following what's called a power law. This pattern was consistent with what theoretical models predicted for a halo formed through hierarchical assembly, the gradual merging of smaller systems over billions of years, but the data also showed deviations from perfect smoothness. There were regions where the density was slightly higher than expected, and others where it was lower. These lumps and gaps were the fingerprints of past mergers, the remnants of satellite galaxies that had been absorbed but not yet fully mixed into the halo. The chemical composition of halo stars provided another crucial piece of information. By analyzing the spectra of individual stars, astronomers could measure the abundances of various elements: iron, magnesium, calcium, and others. Halo stars were consistently metal poor, meaning they had much lower abundances of heavy elements compared to stars in the disk. This confirmed that they were ancient, formed early in the universe's history before many generations of stars had enriched the interstellar medium with heavy elements. But there was also variation. Some halo stars were extremely metal poor, with less than 1,000th the iron abundance of the Sun, while others had somewhat higher metallicities. This spread suggested that the halo was built from multiple populations of stars, each with its own chemical history. By combining position, velocity, and chemical composition, astronomers could identify distinct substructures in the halo. These were groups of stars that moved together and shared similar chemical properties. One of the largest such structures was discovered in data from the Sloan Digital Sky Survey. It was called the Sagittarius Stream, the tidal debris of the Sagittarius dwarf galaxy, a small galaxy currently being torn apart by the Milky Way's gravity. The stream wrapped around the entire galaxy, passing above the disk in one direction and below it in the other, forming a nearly complete loop. Its stars could be traced across huge swaths of the sky, and their motions revealed the orbit of the original dwarf galaxy. Other streams were more subtle, visible only as slight overdensities in the distribution of stars. The Orphan Stream, for example, had no clearly identified parent object. It was a ribbon of stars with no obvious source, suggesting that the galaxy it came from had been completely disrupted long ago. The Helmi Stream was another example, named after the astronomer who discovered it. These streams crisscross the halo, each one marking the path of a satellite that had been accreted in the past. By cataloguing them, astronomers could reconstruct the merger history of the Milky Way, counting how many satellites had been absorbed and when. The data also revealed the structure of the stellar halo in 3 dimensions. It was not perfectly spherical. Instead, it was somewhat flattened, with a shape described as an oblate spheroid. This flattening suggested that the halo had some residual rotation, perhaps inherited from the merger events that built it. The degree of flattening varied with distance. The inner halo was more spherical, while the outer halo showed more asymmetry and structure. This variation hinted at different formation mechanisms for the inner and outer regions, with the inner halo built from mergers that occurred early in the galaxy's history, and the outer halo shaped by more recent accretion events. Gas in the halo showed its own patterns. Radio surveys mapped neutral hydrogen clouds extending far above and below the disk. Some of these clouds were associated with known structures, like the Magellanic Stream trailing behind the large and small Magellanic Clouds. Others were isolated high-velocity clouds with no obvious connection to any satellite galaxy. Their velocities were too high to be consistent with simple rotation around the galactic center. They had to be either infalling gas from the intergalactic medium or gas expelled from the disk that was now falling back. X-ray observations revealed the distribution of hot gas in the halo. This gas formed a diffuse atmosphere, sometimes called the circumgalactic medium, surrounding the disk. Its temperature varied, with some regions reaching several million degrees. The hot gas emitted X-rays through thermal radiation, and by mapping this emission, astronomers could estimate the total mass of gas in the halo. The results suggested that there was as much gas in the halo as in the disk itself, perhaps even more. This was a surprise. It meant that a significant fraction of the galaxy's baryonic matter, the ordinary matter made of atoms, was not in stars or the cold gas clouds where stars form, but in this hot diffuse phase. The X-ray data also showed structures within the hot gas. There were regions of enhanced emission above and below the galactic center, coinciding with the Fermi bubbles discovered in gamma rays. The X-ray emission traced the edges of the bubbles, showing where hot gas had been swept up by the expanding structure. This correlation between X-ray and gamma ray emission provided important clues about the bubble's origin. It suggested they were created by a powerful outflow from the galactic center, perhaps driven by an active phase of the central black hole or by a burst of supernova activity. The outflow pushed gas outward, creating shock waves that heated the gas and accelerated particles to high energies. Ultraviolet spectroscopy added detail to this picture. By observing the absorption lines imprinted on the light from background quasars, astronomers could probe the gas along specific sightlines through the halo. These observations showed that the halo contained multiple phases of gas with different temperatures and ionization states. There was cool neutral gas, warm ionized gas with temperatures of tens of thousands of degrees, and hot, highly ionized gas with temperatures of millions of degrees. Each phase occupied a different volume, with the cool gas concentrated in clouds and filaments, while the hot gas filled most of the volume. The data also revealed the kinematics of the halo gas, how it moved. Some of the gas was rotating with the disk, carried along by the galaxy's overall spin, but other gas showed more complex motions. There were inflows, streams of gas falling toward the disk, and outflows, gas being expelled upward and downward by supernova and stellar winds. The balance between inflows and outflows determined whether the disk gained or lost mass over time, which in turn affected the rate of star formation. Understanding this balance was crucial for understanding how the Milky Way evolved. One of the most important datasets came from the Gaia satellite, a European Space Agency mission launched in 2013. Gaia's goal was to measure the positions, motions, and brightnesses of over 1 billion stars with unprecedented precision. By observing each star multiple times over several years, Gaia could detect tiny shifts in their positions caused by their motion through space. These measurements, combined with spectroscopic observations from ground-based telescopes, allowed astronomers to determine the three-dimensional velocities of millions of halo stars. The Gaia data revolutionized the study of the halo. With precise velocities, astronomers could trace back the orbits of individual stars and identify groups that moved together. They discovered new stellar streams that had been too faint or too diffuse to detect before. They found shells and clouds of stars, the debris of ancient mergers, and they uncovered evidence of a massive collision that occurred about 10 billion years ago, when the Milky Way merged with a galaxy now called Gaia Enceladus, or the Sausage Galaxy. This merger was so significant that it reshaped the inner halo, scattering billions of stars into chaotic orbits and possibly even disrupting the disk. The data showed that the space above and below the disk was not a simple, uniform region. It was structured, layered, filled with the remnants of past events. Every stream, every cloud, every variation in density or composition told part of the story. The halo was a palimpsest, a manuscript that had been written on, erased, and written on again, with traces of each previous version still visible. By carefully analyzing the data, astronomers could peel back those layers, reconstructing the history of the galaxy merger by merger, accretion event by accretion event. But even with all this data, mysteries remained. The exact distribution of dark matter in the halo was still uncertain. The nature of the high-velocity clouds was debated. The origin of the Fermi bubbles was not fully understood, and new questions emerged. Were there structures in the halo that we still hadn't detected? How much gas was there in total? And how did it flow? What happened during the galaxy's most dramatic mergers? And how did they shape the halo we see today? The data provided answers, but it also raised new questions, pushing the investigation deeper. When the announcement came in November of 2010, it felt like the discovery of a new continent. The Fermi Gamma-Ray Space Telescope had revealed two enormous structures extending above and below the Milky Way's center. each one reaching 25,000 light-years into space. Together, they formed a figure-8 shape, a pair of lobes symmetric around the galactic plane. They glowed in gamma rays, the highest energy light in the universe, radiation so energetic it could only be produced by the most violent cosmic processes. And they were huge, spanning 50,000 light-years from top to bottom, roughly half the diameter of the entire visible galaxy. These were the Fermi bubbles, and their discovery changed everything we thought. We knew about the space above and below our galactic home. The bubbles had been hiding in plain sight, or rather, hiding in wavelengths we couldn't see. Gamma rays don't penetrate Earth's atmosphere, so for most of human history, this entire spectrum was invisible to us. Even after we launched satellites capable of detecting gamma rays, the bubbles remained hidden because they were so large and so diffuse. They filled such a huge portion of the sky that they looked like part of the background, a gradual variation in the gamma ray emission that could easily be mistaken for instrumental effects or contamination from other sources. It took careful analysis, years of accumulated data, and sophisticated statistical techniques to subtract away all the known sources and reveal the underlying structure. The team that discovered them, led by Doug Finkbeiner at the Harvard-Smithsonian Center for Astrophysics, had been working with Fermi data for 2 years. They were looking for signs of dark matter annihilation, a process where dark matter particles collide and destroy each other, producing gamma rays as a byproduct. They didn't find dark matter, at least not definitively, but they found something arguably more interesting. As they processed the data, subtracting the bright emission from pulsars and the diffuse glow from cosmic rays, 2 symmetric structures emerged from the noise. They were so clear, so well defined, that there was no doubt they were real. The edges of the bubbles were remarkably sharp for such large structures. In most cosmic objects, boundaries are gradual and fuzzy, blending smoothly into their surroundings. But the Fermi bubbles had edges you could trace, regions where the gamma ray intensity dropped off relatively quickly. This sharpness suggested that the bubbles were bounded by shock waves, expanding shells of gas that marked the interface between the hot interior and the surrounding halo. It also suggested that the bubbles were relatively young, in cosmic terms. If they had been around for billions of years, those sharp edges would have blurred and dispersed. But they hadn't. The bubbles had to be only a few million years old, perhaps 10 million at most. The gamma ray emission itself came from a process called inverse Compton scattering. High-energy electrons within the bubbles collided with lower-energy photons, transferring some of their energy and boosting the photons into the gamma ray range. For this to work, there had to be enormous numbers of energetic electrons filling the bubbles, electrons moving at speeds very close to the speed of light. These electrons had to have been accelerated by something, some powerful mechanism that could inject energy across such a vast volume. The question was, what? The position of the bubbles provided an important clue. They were centered on the galactic nucleus, the very heart of the Milky Way, where a supermassive black hole lurked. This black hole, called Sagittarius A star, or STIR, a star for short, has a mass about 4 million times that of the Sun. Today, it's relatively quiet, accreting only small amounts of matter and producing faint emissions across the spectrum. But black holes are not always quiescent. Under the right conditions, when they have enough gas or stars to feed on, they can become extraordinarily active, releasing vast amounts of energy in the form of jets and winds. Perhaps STIR A star had gone through such an active phase in the relatively recent past. The idea wasn't as far-fetched as it might sound. Many galaxies have active galactic nuclei, central black holes that are currently accreting large amounts of matter and blazing with energy. These active nuclei produce powerful jets that shoot outward along the rotation axis of the black hole, perpendicular to the accretion disk. The jets can extend for millions of light years, ploughing through the intergalactic medium and creating enormous lobes of radio emission. The Fermi bubbles looked similar in many ways, just smaller and less energetic. Perhaps they were the remnants of a period when the Milky Way's central black hole was more active, a time when it behaved more like the active nuclei we see in other galaxies. If this were true, the bubbles would be evidence of a dramatic event in the galaxy's recent history. Sometime between 1 and 10 million years ago, something fed the black hole. Perhaps a massive cloud of gas fell into the galactic center, or perhaps a cluster of stars wandered too close and was torn apart by tidal forces. As material spiraled into the black hole, it would have heated up, releasing energy in the form of radiation and driving powerful winds. These winds would have blown outward from the nucleus, expanding into the halo above and below the disk. The expanding wind would have swept up gas, creating the shock waves that now form the bubble edges and accelerated electrons to high energies, producing the gamma-ray glow we see today. But there was another possibility. The bubbles might not have been created by the black hole at all. They might have been produced by a starburst, a period of intense star formation near the galactic center. If a large amount of gas accumulated in the central region and collapsed to form stars all at once, many of those stars would have been massive, hot, and short-lived. Within a few million years, they would have exploded as supernovae, each one releasing as much energy as the sun produces in its entire lifetime. If enough supernovae went off in a short period, their combined energy could have driven a galactic wind, carving out the bubbles we see today. Distinguishing between these two scenarios, black hole outburst versus starburst, was difficult. Both could produce structures that looked similar. The energetics were comparable, the timescales were right, and both mechanisms were known to occur in other galaxies. Symmetry and their alignment with the galactic rotation axis. A wind driven by an accreting black hole would naturally flow along the path of least resistance, perpendicular to the dense disk. Others pointed out that star formation near the galactic center could also produce a symmetric outflow if the stars formed in a ring or disk-like structure. Additional observations provided more clues. Follow-up studies using other instruments revealed that the Fermi bubbles were not just visible in gamma rays. They also showed up in X-rays, radio waves, and microwave emission. Each wavelength revealed a different aspect of the structure. The X-ray emission came from hot gas at the edges of the bubbles, heated to temperatures of millions of degrees by shock waves. The radio emission traced lower energy electrons spiraling around magnetic field lines, and the microwave observations detected a phenomenon called the haze, a diffuse glow of emission filling the region where the bubbles were located. These multi-wavelength observations constrained the physics of the bubbles. The X-ray emission showed that there was about 10 million solar masses of hot gas associated with the structure, gas that had been swept up and heated by the expanding wind. The radio data revealed that the magnetic field within the bubbles was relatively strong, about 10 microgauss, comparable to the field in the galactic disk. This strong field suggested that the bubbles were not just empty cavities but filled with magnetized plasma, gas, where the charged particles moved along magnetic field lines. The shape of the bubbles was also informative. They were not perfectly spherical but elongated, stretching farther vertically than horizontally. This elongation made sense if they were produced by a wind blowing perpendicular to the disk. As the wind expanded, it would encounter less resistance above and below the disk, where the gas density was lower than in the plane itself, where the disk's gravity held gas more tightly. The result would be a preferential expansion in the vertical direction, creating the elongated lobes we see. The Fermi bubbles also had structure within them. They were not uniformly bright but showed variations in intensity, with some regions glowing more strongly than others. There were filaments, narrow features where the emission was enhanced, and there were regions that looked like shells or arcs. These features suggested that the bubble's interiors were not calm but turbulent, filled with eddies and flows that mixed the gas and redistributed the energetic particles. The turbulence might have been driven by the original explosion, or it might have been generated by instabilities at the bubble edges, where the fast-moving interior gas met the slower-moving halo. One of the most intriguing features was a narrow structure running along the bubble's eastern edge, called the Fermi edge. This feature was sharper and brighter than the rest of the bubble boundary, suggesting that something special was happening there. One possibility was that the bubble was running into a pre-existing cloud of dense gas, creating a particularly strong shock wave. Another was that the magnetic field had a different orientation at that location, affecting how particles were accelerated and how they radiated. The discovery of the Fermi bubbles opened up entirely new questions about the galactic center and the space above and below the disk. If the Milky Way could produce such a dramatic outburst, what did that mean for its past? How often did these events occur? Was this a one-time fluke, or was it part of a cycle with the black hole alternating between active and quiescent phases? And what effects did these outbursts have on the galaxy as a whole? Did they regulate star formation, expelling gas that would otherwise collapse into stars? Did they enrich the halo with heavy elements, mixing material from the disk into the larger structure? The bubbles also raised questions about the nature of the halo itself. Before their discovery, the space above and below the disk was thought to be relatively passive, a region where old stars drifted quietly and dark matter dominated. But the bubbles showed that this region could be shaped by energetic processes, by explosions and winds that reached far beyond the disk. The halo was not a graveyard but an active participant in the galaxy's evolution. It was a place where the past still echoed, where ancient violence left visible scars. As astronomers continued to study the Fermi bubbles, they realized that similar structures might exist in other galaxies. In some cases, they'd been seen before but not recognized for what they were. Radio observations of edge-on spiral galaxies often showed lobes or plumes extending above and below the disk, features that had been attributed to various causes but were now understood as possible analogues to the Fermi bubbles. The Milky Way was not unique. Many galaxies might go through episodes of activity that produce such structures, and understanding them was key to understanding galactic evolution in general. The deeper mystery, then, was not just what the Fermi bubbles were, but what they revealed about the nature of galaxies. They showed that galaxies were not static, stable systems, but dynamic environments where dramatic events could reshape vast regions. They showed that the black holes at galactic centers, even relatively quiet ones like Skir A star, could have violent pasts. And they showed that the space above and below the disk, the vertical dimension we'd overlooked for so long, was an essential part of the story. The Milky Way breathed, and the Fermi bubbles were evidence of one particularly powerful exhalation, a moment when the galaxy expelled matter and energy into the halo, altering its structure in ways that persisted for millions of years. The discovery of the Fermi bubbles forced astronomers to reconsider the Milky Way's history. The bubbles, galaxy we lived in, the one we thought we knew, had a violent past. Something had happened at its center, something powerful enough to carve enormous cavities into the halo and fill them with high-energy radiation. This wasn't a minor event, a single supernova, or a small outburst. This was a cataclysm, an explosion or wind strong enough to affect the structure of the entire galaxy. Understanding what caused it became one of the most important questions in galactic astronomy. The answer would reveal not just what happened, but what the Milky Way was capable of, what forces lurked at its heart. The timing of the event could be estimated from the bubble's properties. Their size, about 25,000 light-years from the galactic plane, combined with the speed at which the gas was moving, about 1,000 kilometers per second, suggested they were between 2 and 10 million years old. That was recent in cosmic terms, a blink of an eye compared to the galaxy's age of over 13 billion years. It meant that whatever caused the bubbles happened in an era when the solar system already existed, when Earth was much as it is today. If we could have observed the galactic center from a distance at that time, we would have seen something extraordinary, a blaze of energy erupting from the nucleus and expanding into space. The energy required to create the bubbles was staggering. Estimates suggested it would take the equivalent of 100,000 supernovae, all exploding within a relatively short time, perhaps a million years or less. Alternatively, if the energy came from the black hole, a star would have had to accrete about 100,000 solar masses of material, converting a fraction of that mass into energy through the process of accretion. Either way, the event released roughly 10 to the 56 ergs of energy, a number so large it's almost meaningless without comparison. It's about 1% of the energy the Sun will produce over its entire 10 billion year lifetime, released in a cosmic instant. The black hole hypothesis had some appealing features. Black holes are incredibly efficient at converting mass into energy. As matter spirals inward, falling through the intense gravitational field, it heats up and radiates. About 10% of the infalling mass can be converted to energy, far more efficient than nuclear fusion in stars. And black holes naturally produce jets and winds, outflows of matter and energy that stream away from the accretion disk along the rotation axis. Many active galaxies show exactly this behavior, with jets extending millions of light years into space. The Fermi bubbles could be the scaled-down version, the remnant of a time when a star was more active. But what would have triggered such activity? Today, the central black hole is relatively starved. There's not much gas near it, and it accretes only small amounts of material, producing faint emissions. But the environment near the galactic center is chaotic. There are millions of stars packed into a small volume, orbiting at high speeds. Occasionally, stars pass close enough to the black hole to be disrupted by tidal forces. When that happens, the star is torn apart, and its gas forms an accretion disk around the black hole. For a brief period, the black hole feeds, and its luminosity spikes. Perhaps the Fermi bubbles were created by a series of such tidal disruption events, multiple stars falling into the black hole over a short period. Alternatively, a large cloud of gas might have fallen into the central region. The galactic center is not devoid of gas. There are molecular clouds, dense clumps of hydrogen, and other molecules orbiting near the nucleus. If one of these clouds happened to lose angular momentum, perhaps through a collision with another cloud, or through gravitational interactions with stars, it could fall toward the black hole. As it fell, it would be stretched and heated, eventually forming an accretion disk. The black hole would feed for as long as the gas supply lasted, perhaps a few million years, driving winds and jets that carved out the bubbles. The starburst hypothesis offered a different picture. Near the galactic center, there's a region called the Central Molecular Zone, an area a few hundred light years across that contains dense clouds of gas. If conditions changed, if the gas became unstable or was compressed by some external force, it could collapse to form stars at a prodigious rate. Calculations suggested that forming about 100 million solar masses of stars within a few million years would produce enough supernovae to create the Fermi bubbles. This was a lot of stars, but not impossible. Starburst galaxies in the distant universe form stars at even higher rates. The challenge with the starburst model was explaining what triggered the burst. Star formation requires dense gas, and it requires that gas to be cool enough to collapse under its own gravity. In the harsh environment near the galactic center, where radiation is intense and tidal forces are strong, forming stars is difficult. But perhaps a merger event helped. If a smaller galaxy fell into the Milky Way and passed near the center, its gravity could have stirred up the gas, compressing it and triggering a wave of star formation, or perhaps a spiral density wave. One of the patterns that creates the galaxy's spiral arms passed through the central region and compressed the gas there. Distinguishing between these scenarios required looking for additional evidence. One approach was to search for remnants of the original event. If the black hole had been active, there might be echoes, light from the outburst that scattered off distant clouds and was now reaching us with a delay. Astronomers looked for such echoes in X-ray observations, but found nothing definitive. If there had been a starburst, there might be a population of young stars near the galactic center. Stars formed during the event. Infrared observations did reveal some young stellar clusters, but it was hard to tell if they were associated with the bubble-forming event or were simply part of the ongoing star formation in that region. Another clue came from the composition of the gas in the bubbles. If the bubbles were inflated by a starburst, the gas should be enriched with heavy elements, the products of supernova explosions. If they were inflated by black hole winds, the composition might be more typical of the surrounding halo. Spectroscopic observations of the X-ray emitting gas at the bubble edges showed some enrichment, but the measurements were difficult and the results uncertain. The debate continued, with different groups favouring different explanations. What everyone agreed on was that the event represented a turning point in how we understood the Milky Way. Before the discovery of the Fermi bubbles, our galaxy seemed stable and unremarkable, a typical spiral going about its business of slowly forming stars. But the bubbles showed that even normal galaxies could experience dramatic outbursts, events that reshaped their structure on large scales. The distinction between normal and active galaxies was not as clear as we'd thought. It might simply be a matter of timing. Perhaps all spirals go through active phases occasionally, and we happen to be seeing the Milky Way during a quiescent period, with only the fading remnants of its last outburst still visible. This realization had implications for understanding galaxy evolution in general. Astronomers had long known that feedback, the return of energy from stars and black holes to the surrounding gas, played a crucial role in regulating star formation. Without feedback, all the gas in a galaxy would collapse into stars too quickly, forming a galaxy much more massive and much less structured than what we observe. Feedback prevents this by heating and expelling gas, slowing down star formation and allowing galaxies to evolve gradually over billions of years. The Fermi bubbles were a dramatic example of feedback in action, a single event powerful enough to affect the entire halo. The bubbles also changed how astronomers thought about the space above and below the disk. Before, this region was seen mainly as a repository for old stars and dark matter, a passive halo surrounding the active disk. But the bubbles showed that energy and matter could be transported from the disk, or from the galactic center, into the halo, filling it with hot gas and high-energy particles. The halo was not separate from the disk, but connected to it through flows of matter and energy. The galaxy was an integrated system, with different components influencing each other across vast distances. The ancient explosion that created the Fermi bubbles was a reminder that the cosmos is not static. On human timescales, the stars seem fixed, the galaxy unchanging, but over millions of years, dramatic events reshape cosmic structures. Stars explode, black holes flare, galaxies merge, and the space above and below the disk, the vertical dimension we'd barely noticed, bears the scars of these events. The Fermi bubbles were one such scar, a monument to a moment of violence that occurred just a few million years ago, when something at the heart of the Milky Way unleashed a torrent of energy that's still echoing through the halo today. As astronomers continued to study the bubbles, they realized that this might not have been a unique event. There could have been earlier outbursts, even more powerful ones, whose remnants had long since faded. The bubbles we see today might be just the most recent in a series of explosive episodes that punctuated the galaxy's history. If so, the Milky Way's past was far more violent than its present suggested, and its future might hold more surprises. The black hole at the center is still there, waiting. The gas in the central molecular zone continues to orbit and evolve. Conditions could change, another cloud could fall in, or another burst of star formation could ignite. The galaxy could breathe again, sending another pulse of energy into the space above and below the disk. The discovery of the Fermi bubbles didn't just reveal something about the halo, it forced astronomers to reconsider the very heart of the galaxy, the supermassive black hole that sits at its center. For years, Sagittarius A star had been viewed as a relatively quiet object, a dormant giant that occasionally snacked on passing gas clouds, but never did anything truly dramatic. The Fermi bubbles changed that perception entirely. They were evidence that Skra, a star, or the region around it, was capable of extraordinary violence. The consequences of this realization rippled through our understanding of galactic centers, black hole behavior, and the relationship between a galaxy and its nucleus. Black holes had always been mysterious objects, predicted by Einstein's theory of general relativity, but not directly observed until the late 20th century. The idea that a supermassive black hole lurked at the center of the Milky Way was controversial when it was first proposed in the 1970s, but over the following decades, evidence accumulated. Astronomers tracked the orbits of stars near the galactic center, stars moving at speeds of thousands of kilometers per second. These stars were orbiting something massive and compact, something that didn't emit any light of its own. The only explanation that made sense was a black hole, and based on the stellar orbits, its mass had to be about 4 million times that of the Sun. By the early 2000s, the case for a central black hole was ironclad. Observations using infrared telescopes, which could see through the dust that obscured the galactic center, revealed stars orbiting in tight ellipses around a point in space that appeared empty. The closest approach of these stars brought them within just a few light hours of the black hole, a tiny distance on cosmic scales. At these distances, the gravitational pull was so strong that the stars moved at a significant fraction of the speed of light. Their orbits followed the predictions of general relativity precisely, confirming not just the existence of the black hole but the correctness of Einstein's theory in this extreme environment. But despite its enormous mass, Skra, a star, was remarkably dim. It emitted only faint radiation, mostly at radio and X-ray wavelengths. This faintness suggested that the black hole was not accreting much matter. Compared to the active galactic nuclei seen in other galaxies, where central black holes blaze with the luminosity of billions of stars, Skra, a star, was a whisper. It was accreting perhaps 1/10,000th of an Earth mass per year, a tiny trickle of gas falling into the black hole's maw. This led to the view that our galaxy's black hole was essentially dormant, sleeping peacefully at the center while the rest of the galaxy went about its business. The Fermi bubbles shattered this picture. They showed that even if Skra star was quiet now, it hadn't always been. At some point in the past few million years, it had been far more active, either feeding on a substantial amount of material or participating in events that released enough energy to carve enormous cavities in the halo. This meant that black holes could switch between quiescent and active states on timescales that were short by cosmic standards. A black hole that appeared dormant might simply be between meals, waiting for the next influx of gas. This variability had important implications for understanding how black holes grow. Supermassive black holes, found at the centers of most large galaxies, are millions to billions of times more massive than the Sun. They didn't start out that way. They must have grown over time by accreting matter and by merging with other black holes during galaxy collisions. But the process of growth is episodic. A black hole feeds only when there's gas or stars nearby to consume. Most of the time, the central region of a galaxy is relatively empty, swept clear by previous episodes of activity. But occasionally, something changes. A gas cloud falls in, a star passes too close, or a galaxy merger funnels material toward the center. The black hole wakes up, feeds, and grows. The Fermi bubbles suggested that the Milky Way's black hole had experienced such an awakening in the recent past. If the bubbles were created by an outburst from Skua A star, then the black hole must have accreted at least 100,000 solar masses of material, perhaps much more if the conversion of mass to energy was not very efficient. This was a substantial meal, enough to increase the black hole's mass by a few percent, and it would have been a spectacular event. As the gas spiraled inward, it would have heated to millions of degrees, emitting intense X-rays and ultraviolet radiation. Some of the gas would have been expelled in powerful winds, streaming away from the black hole along its rotation axis. These winds would have ploughed into the surrounding gas, driving shock waves and creating the bubbles we see today. But there were puzzles. If Skua A star had been so active, why didn't we see more evidence of it? Where were the remnants of the accretion disk? Where was the young stellar population that might have formed from the disrupted gas? And why was the black hole so quiet now? One possibility was that the accretion was brief and intense, a few million years of activity followed by a rapid decline as the gas supply was exhausted. Another was that the black hole's activity was cyclic, with long quiescent periods punctuated by brief outbursts. If the cycle time was tens of millions of years, we might simply be seeing the galaxy during a quiet phase. Another consequence of rethinking the galactic center was recognizing its complexity. The central region of the Milky Way is not just a black hole sitting in empty space. It's a dense, chaotic environment filled with stars, gas clouds, magnetic fields, and radiation. Within the innermost light year, there are millions of stars packed together, a stellar density 1,000,000 times higher than in our neighborhood. These stars orbit the black hole in a complex dance, their paths shaped by the gravity of the black hole and by gravitational interactions with each other. Occasionally, two stars collide, merging to form a more massive star or producing a burst of debris. The gas in the central region is equally complex. There are cold molecular clouds, dense clumps of gas that contain the raw materials for star formation. There are hot ionized regions, heated by radiation from nearby stars, and there are streams and filaments, structures shaped by magnetic fields and tidal forces. This gas is constantly in motion, falling inward toward the black hole, being swept up by stellar winds, or being blown outward by supernova explosions. The environment is far from static. One particularly interesting feature is the circumnuclear disk, a ring of dense gas orbiting the galactic center at a distance of a few light years. This disk contains about 100,000 solar masses of material, enough to feed the black hole for millions of years if it fell inward. But the disk is stable, rotating too quickly to collapse directly. For gas to reach the black hole, it has to lose angular momentum, perhaps through interactions with magnetic fields or through the effects of turbulence. Understanding how this happens is key to understanding when and how the black hole feeds. The rethinking of the galactic center also had implications for understanding the Milky Way's future. If the black hole could become active again, what would trigger the next outburst? One possibility involved the ongoing interaction with satellite galaxies. The Magellanic Clouds, for example, are gradually spiraling toward the Milky Way, and in a few billion years, they may merge with it. As they approach, their gravity could perturb gas in the galactic disk, funneling it toward the center and providing fuel for the black hole. A merger with Andromeda, expected in about 4 billion years, would have an even more dramatic effect. The collision would send shock waves through both galaxies, compressing gas and triggering star formation. Some of that gas would inevitably fall toward the merged galaxy's center, where the two supermassive black holes would themselves merge, creating a monster black hole and likely driving a powerful outburst. But even without mergers, the black hole's activity could resume. Gas clouds continue to orbit near the galactic center, and some of them are on trajectories that will bring them close to the black hole. In 2011, astronomers discovered a cloud called G2 heading towards Skara star on what looked like a collision course. Initial predictions suggested the cloud would be torn apart when it reached its closest approach in 2014, potentially feeding the black hole and triggering a burst of activity. The astronomical community watched with anticipation, hoping to see the black hole light up. In the end, G2 survived its encounter more or less intact, passing by without producing the dramatic fireworks astronomers had hoped for. But the event showed that such close encounters do happen, and one day a cloud or star might not be so lucky. The Fermi bubbles also changed how astronomers thought about feedback from galactic centers. Feedback is the process by which energy released by stars or black holes affects the surrounding gas, heating it, stirring it, or expelling it from the galaxy. This feedback plays a crucial role in regulating star formation and shaping galaxy evolution. Too much star formation can be self-limiting, as the massive stars that form quickly explode as supernovae, blowing away the gas needed to form more stars. Similarly, an active black hole can heat or expel gas from the central region, starving itself and shutting down its own growth. The Fermi bubbles were a dramatic example of feedback in action. The energy released during the bubble-forming event had profound effects on the gas in the halo. It heated millions of solar masses of gas to temperatures of millions of degrees. It accelerated electrons to relativistic speeds, and it drove a wind that carried gas far from the galactic center, possibly even expelling it from the galaxy entirely. This feedback affected not just the immediate surroundings of the black hole, but the entire galaxy, reaching out to distances of tens of thousands of light years. Understanding the interplay between black holes and their host galaxies became a major focus of research. It turned out that black holes and galaxies were deeply connected. The mass of a galaxy's central black hole correlated with the properties of the galaxy's bulge, the central concentration of stars. More massive bulges had more massive black holes, suggesting that the two grew together. This correlation implied that black holes and galaxies co-evolved, each influencing the other's development. Feedback from black holes might regulate galaxy growth, preventing galaxies from becoming too massive, and galaxy mergers might trigger black hole growth, funneling gas toward the center and feeding the black hole. The consequence of rethinking the galactic center, then, was a new appreciation for the dynamic relationship between a galaxy and its nucleus. The center was not a passive component, but an active player in the galaxy's evolution. Its outbursts shaped the halo, its gravity organized the orbits of stars, and its feedback regulated star formation. The space above and below the disk bore the marks of this activity, carved by winds and filled with the debris of ancient explosions. The Milky Way was not just a disk with a black hole at its center. It was an integrated system where events at the nucleus could affect structures hundreds of thousands of light years away. The Fermi bubbles were not just interesting structures in themselves. They were evidence of a process that had shaped the Milky Way over billions of years. The impact of the bubble-forming event extended far beyond the immediate vicinity of the galactic center. It affected the distribution of gas in the halo, the chemistry of the interstellar medium, and possibly even the rate of star formation throughout the galaxy. Understanding this impact meant understanding how galaxies breathe, how they cycle matter between different regions, and how energy released in one part of the system can influence regions far away. The bubbles were the most visible sign of this process, but they were part of a much larger story about galactic winds and the vertical transport of matter and energy. Galactic winds are outflows of gas driven by energy released in the galaxy. This energy can come from supernovae, from stellar winds, or from black hole activity. As stars form and evolve, they return energy to their surroundings. Massive stars emit powerful winds during their lifetimes, and when they die, they explode as supernovae, each one releasing as much energy as the sun produces in 10 billion years. If enough stars form in a small region, the combined energy from their winds and explosions can drive gas out of that region, creating a bubble or a larger outflow. In the disk of the Milky Way, this process happens continuously. Young stars form in clusters, dozens or hundreds of them born from the same molecular cloud. The most massive stars live only a few million years, and when they explode, their supernovae go off almost simultaneously, creating a superbubble. These superbubbles can grow to hundreds of light years across, and if they form near the edge of the disk, where the gas layer is thin, they can break out, venting hot gas into the halo. This is called a galactic fountain, and it's one of the primary mechanisms by which matter and energy are transported vertically through the galaxy. The Fermi bubbles were a more extreme version of this process. Instead of being driven by star formation in the disk, they were driven by activity at the galactic center, either from the black hole or from a massive starburst. But the physics was similar. Energy was released, gas was heated and accelerated, and a wind blew outward into the halo. The wind swept up surrounding gas, creating the shock waves that now form the bubble edges, and it carried material from the galactic center into the halo, mixing it with the existing gas and altering the halo's composition. This mixing had important consequences. The gas near the galactic center is enriched with heavy elements, the products of generations of stellar nucleosynthesis. When that gas was expelled into the halo, it carried those heavy elements with it. Measurements of the gas at the edges of the Fermi bubbles showed elevated abundances of elements like oxygen, neon, and iron, confirming that the bubbles contained processed material from the galactic center. This enrichment meant that the halo was not chemically isolated from the disk. Matter cycled between the two, with winds carrying enriched gas upward and gravity pulling gas back down. The impact of this cycling extended to star formation. The rate at which a galaxy forms stars depends on the amount of cold gas available. If gas is heated and expelled, star formation slows down. If gas accumulates, star formation speeds up. By driving a powerful wind, the bubble-forming event removed gas from the galactic center and possibly from the entire disk, at least temporarily. This would have reduced the star formation rate, regulating the galaxy's growth. Over millions of years, some of the expelled gas would cool and fall back, raining down onto the disk and replenishing the reservoir for future star formation. But the cycle took time, creating a rhythm of activity and quiescence. The Fermi bubbles also affected the magnetic field in the halo. Magnetic fields are frozen into the gas, meaning that when gas moves, it carries the magnetic field with it. As the wind expanded from the galactic center, it dragged magnetic field lines outward, stretching them into the halo. The field lines traced the flow of gas, creating a complex web that extended far above and below the disk. This magnetized plasma could trap cosmic rays, high-energy particles that stream through the galaxy. Instead of escaping immediately into intergalactic space, the cosmic rays would spiral along the magnetic field lines, spending more time in the halo and contributing to the heating and ionization of the gas. Another impact involved the pressure of the hot gas in the bubbles. Pressure is force per unit area, and hot gas at millions of degrees exerts substantial pressure on its surroundings. The bubbles pushed outward against the surrounding halo, compressing the gas at their edges and creating dense shells. These shells were sites where gas could cool and potentially form stars. Some astronomers speculated that the compression caused by the expanding bubbles might have triggered star formation in the halo, creating small populations of stars far from the disk. These would be unusual stars, formed in an unusual environment, and finding them would provide strong evidence for this process. The bubbles also served as a reservoir of energy. Even millions of years after their formation, they still glowed with gamma rays and X-rays, radiation produced by the energetic particles within them. This energy was slowly dissipated, absorbed by the surrounding gas, or radiated away into space. But while it lasted, it affected the thermal balance of the halo, keeping large volumes of gas hot and ionized. This changed the halo's structure, creating regions that were less dense but more extended than they would otherwise be. The long-term impact of the bubble-forming event was harder to assess. On timescales of tens or hundreds of millions of years, the bubbles would fade. The shock waves would slow down and merge with the surrounding gas. The energetic particles would lose their energy through radiation and interactions. Eventually, the bubbles would disappear, leaving behind only subtle traces in the distribution and chemistry of halo gas. But their effects would persist. The gas they expelled might take hundreds of millions of years to fall back, if it ever did. The heavy elements they carried into the halo would mix with the existing gas, altering its composition permanently, and the compression they caused might have seeded structures that would evolve over time. Comparing the Milky Way to other galaxies provided additional insights into the impact of such events. Many spiral galaxies showed evidence of galactic winds. In edge-on spirals, where we see the disk from the side, winds often appeared as plumes or lobes of emission extending above and below the plane. These plumes were visible in X-rays, in hydrogen, alpha emission, and sometimes in radio waves. They looked similar to the Fermi bubbles. Though not always as large or as symmetric, this suggested that galactic winds were common, a natural part of spiral galaxy evolution. Every galaxy with active star formation or an active nucleus would experience episodes of feedback, driving winds that shaped the halo. The impact of these winds on galaxy evolution was profound. Without feedback, galaxies would convert their gas into stars too efficiently, forming massive systems dominated by old stars with little ongoing star formation. But feedback slowed this process down. It heated gas, making it harder to collapse. It expelled gas, removing it from the star-forming regions. And it enriched the gas, seeding it with heavy elements that affected how future stars would form. The result was galaxies like the Milky Way, systems that had been forming stars steadily for billions of years, converting their gas gradually rather than all at once. The Fermi bubbles, then, were not just isolated features. They were part of a continuous process of energy and matter exchange between different parts of the galaxy. The disk, the halo, and the galactic center were all connected, linked by flows of gas, magnetic fields, and energetic particles. Energy released at the center propagated outward, heating the halo and driving winds. Gas fell inward, feeding star formation and providing fuel for future outbursts. The galaxy operated as a single integrated system, with feedback loops regulating its behavior over cosmic time. This realization changed how astronomers modeled galaxy evolution. Early models treated galaxies as closed boxes, systems where gas was gradually converted into stars with no exchange with the outside. But observations like the Fermi bubbles showed that this was too simplistic. Galaxies were open systems, constantly exchanging matter and energy with their surroundings. They accreted gas from the intergalactic medium, feeding their star formation. And they expelled gas through winds, enriching the intergalactic medium and regulating their own growth. The boundary between a galaxy and the space around it was not sharp but permeable, with matter flowing in both directions. The space above and below the disk was central to this exchange. It was the region through which winds blew outward and through which gas fell inward. It was where the hot and cold phases of the interstellar medium met and interacted, and it was where the galaxy's history was written, in the form of stellar streams, bubbles, shells, and other structures that recorded past events. By studying this region, astronomers could learn not just about the Milky Way, but about how galaxies in general evolved, how they regulated their growth, and how they interacted with the universe around them. The impact of the Fermi bubbles echoed through time, affecting the galaxy for millions of years after the event that created them. And the event was just one in a long series of feedback episodes that had shaped the Milky Way over its lifetime. Each supernova, each burst of star formation, each period of black hole activity contributed to the vertical transport of energy and matter. The cumulative effect of all these events determined the galaxy's structure, its star formation history, and its chemical evolution. The space above and below the disk was not a passive backdrop but an active participant in the galaxy's life, shaped by the past and shaping the future. Behind every discovery about the space above and below the Milky Way, there were people, not just the famous names that appear in textbooks, but countless astronomers, students, technicians, and dreamers who spent their careers looking upward and downward from the galactic plane, trying to understand what lay in those overlooked directions. Some of them worked for decades on problems that seemed obscure at the time, mapping faint stars that most astronomers ignored, measuring velocities that didn't fit the expected patterns, or proposing theories that challenged conventional wisdom. Their stories are worth telling, not because they're exceptional in the heroic sense, but because they're human. They remind us that science is not a process of inevitable progress but a collective effort, driven by curiosity, persistence, and sometimes stubbornness. Harlow Shapley is often credited as the first astronomer to truly map the vertical dimension of the Milky Way. In the early 20th century, when most astronomers still thought of the galaxy as a relatively small structure, with the sun near its center, Shapley studied globular clusters. These dense spheres of ancient stars were scattered across the sky, but not uniformly. Most of them clustered in one direction, toward the constellation Sagittarius. This asymmetry intrigued Shapley. If the sun were at the center of the galaxy, the globular clusters should be evenly distributed around us. But they weren't. They were concentrated in one hemisphere, suggesting that the center of the galaxy lay in that direction and that we were far from it. Shapley measured the distances to these clusters using a type of variable star called RR Lyrae. These stars pulsate with regular periods, and their intrinsic brightness is known. By comparing their apparent brightness to their intrinsic brightness, Shapley could calculate how far away they were. The results were stunning. The globular clusters were tens of thousands of light-years away, and they formed a roughly spherical distribution centered on a point far from the Sun. This spherical distribution extended far above and below the galactic plane, showing that the Milky Way was not just a flat disk, but a three-dimensional structure with a substantial halo. Shapley's work was revolutionary, but it was also controversial. His distance estimates suggested that the Milky Way was much larger than anyone had thought, about 300,000 light-years across. This turned out to be an overestimate. He hadn't accounted for the dimming effects of interstellar dust. But the basic insight was correct. The galaxy was huge, and we were not at its center. More importantly for our story, the galaxy extended vertically. The globular clusters orbiting far above and below the disk were proof that there was structure in those directions, not just emptiness. But Shapley's work might have been forgotten if not for others who followed. In the mid-20th century, astronomers like Walter Baade studied the different populations of stars in the galaxy. Baade realized that there were two distinct types of stellar populations. Population 1 stars, which were young, metal-rich, and found mostly in the disk, and Population 2 stars, which were old, metal-poor, and found in the halo and bulge. This distinction showed that the galaxy had a history, that it had formed stars in different environments at different times. The halo stars were relics of the galaxy's early days, while the disk stars represented more recent generations. Vera Rubin deserves mention here as well, though her most famous work involved other galaxies. In the 1970s, Rubin and her colleagues studied the rotation curves of spiral galaxies, measuring how fast stars and gas orbited at different distances from the center. They found that the orbital speeds didn't decrease with distance as expected. Instead, they stayed roughly constant, implying the presence of large amounts of unseen mass. This was some of the strongest evidence for dark matter, and it applied to the Milky Way as well as to other galaxies. The halo, both ours and those of other spirals, was dominated by this invisible substance. Rubin's work was painstaking and methodical, requiring hundreds of nights at the telescope, carefully measuring the spectra of faint galaxies. She faced skepticism and discrimination as a woman in a male-dominated field, but her results were undeniable. Jan Oort, the Dutch astronomer, contributed in a different way. In the 1930s and 40s, he studied the dynamics of stars near the Sun. He noticed that stars near the plane oscillated vertically, bobbing up and down as they orbited the galactic center. By measuring these oscillations, Oort could estimate the amount of mass in the disk and halo. He found a discrepancy, evidence that there was more gravitating mass than could be accounted for by visible stars. At the time, he attributed this to faint stars and interstellar matter, but with hindsight, we recognize it as an early hint of dark matter. In more recent decades, the human element of the story includes the teams that built and operated the space telescopes that revealed so much about the halo. The Fermi Gamma Ray Space Telescope, for instance, was the culmination of years of planning, engineering, and collaboration among hundreds of scientists and engineers. Doug Finkbeiner and his colleagues, who discovered the Fermi bubbles, didn't set out specifically to find them. They were looking for signs of dark matter annihilation, a hypothetical process that should produce gamma rays. Instead, they found something no one expected: enormous structures towering above and below the galactic center. The discovery required careful data analysis, sophisticated statistical techniques, and a willingness to believe that a signal so large and obvious had somehow been overlooked. The Gaia mission, launched by the European Space Agency, represents another kind of human achievement. Gaia's goal was to map the positions and motions of over 1 billion stars with unprecedented precision. The data it returned revolutionized our understanding of the Milky Way's structure, revealing stellar streams, shells, and substructures that had never been seen before. But the mission was only possible because of decades of technological development and the dedication of a large team. The scientists who analyzed Gaia's data had to develop new algorithms, new ways of handling enormous datasets, and new methods for extracting patterns from noise. The discoveries came not from a single eureka moment, but from years of patient work. There were also the theorists, the people who tried to make sense of the observations. Simon White and his colleagues developed computer simulations of galaxy formation, modeling how dark matter halos collapse and how galaxies form within them. These simulations showed that hierarchical assembly, the gradual merging of smaller systems into larger ones, naturally produced the structures we see in galactic halos. The stellar streams, the globular clusters, the variations in density, all of these emerged naturally from the simulations. The theorists provided the framework for understanding what the observations meant, connecting individual pieces of data into a coherent story. And there were the observers who spent countless nights at telescopes, often in remote locations, gathering the data that made all this possible. Astronomy is sometimes romanticized as a solitary pursuit, the lone astronomer gazing at the stars. But in reality, it's a deeply collaborative endeavor. Observations are planned months or years in advance. Multiple people work together to operate the telescope, calibrate the instruments, and process the data. Much of the work happens in front of computer screens, analyzing spectra, measuring positions, fitting models to data. It's painstaking and often tedious, but it's essential. The human element also includes the mistakes and dead ends, the ideas that didn't work out. Not every theory about the halo was correct. Not every observation led to a new discovery. Science advances through trial and error, through proposing ideas and testing them against reality. Some of the brightest minds in astronomy spent years pursuing ideas that turned out to be wrong, but even failed. Ideas contributed to progress by ruling out possibilities and forcing people to think harder about the alternatives. What all these people had in common was curiosity. They wanted to understand the universe, to know what lay beyond the familiar, to see what others had overlooked. The space above and below the galactic disk seemed empty and uninteresting to many, but to these astronomers it was a frontier. They saw possibilities where others saw nothing. They asked questions that seemed odd or irrelevant at the time but turned out to be crucial. And they persisted, even when the problems were difficult and the answers were not immediately forthcoming. The story of the halo's exploration is also a story about changing technology. Each new instrument, each new technique, opened up possibilities that didn't exist before. Photography allowed astronomers to image faint stars and measure their positions with precision. Spectroscopy allowed them to measure velocities and chemical compositions. Space telescopes removed the limitations of Earth's atmosphere, revealing wavelengths that were invisible from the ground. Computers made it possible to process vast amounts of data and to run simulations that mimicked the evolution of galaxies over billions of years. Each technological advance brought new discoveries, new questions, and new insights. But technology alone was not enough. It took human creativity to figure out how to use these tools, to design the right observations, to ask the right questions. It took human persistence to work through the difficulties, to troubleshoot problems, to keep going when results were ambiguous or contradictory. And it took human collaboration, the willingness to share data, to build on each other's work, to combine different areas of expertise into a coherent whole. The dreamers who studied the space above and below the Milky Way were not motivated by fame or fortune. Most of them spent their careers in relative obscurity, known only within their small communities of specialists. But they were driven by something deeper, a desire to understand, to see what was really there, to push back the boundaries of the known. They looked at the galaxy not as a flat disk, but as a three-dimensional structure with depth and complexity. They saw the halo not as an afterthought, but as an integral part of the galaxy, a region with its own history and its own mysteries. In the end, the human element of the story reminds us that science is a human endeavor. It's done by people with strengths and weaknesses, with biases and blind spots, with moments of brilliance and moments of confusion. The discoveries we celebrate today were made possible by the work of many, some famous, some forgotten, all contributing in their own ways. The space above and below the Milky Way revealed its secrets slowly, over decades and centuries, because people kept looking, kept measuring, kept thinking. They were the dreamers who imagined that there was more to see, and they were right. For much of the 20th century, the dominant view of the Milky Way was surprisingly simple. It was a disk of stars, gas, and dust, spinning gently through space. The disk was where everything important happened, where stars formed, where the spiral arms traced elegant patterns, where the sun and all the familiar stars resided. The space above and below the disk, if it was considered at all, was seen as mostly empty, a void dotted with a few ancient globular clusters, but otherwise devoid of interest. This view, which we might call the flat galaxy paradigm, was not necessarily wrong, and for decades it shaped how astronomers thought about the Milky Way, influencing what they studied, what questions they asked, and what discoveries they made or missed. The flat galaxy paradigm had deep roots. It arose naturally from the observations available in the early and mid-20th century. When astronomers looked at the Milky Way, as it appeared in the night sky, they saw a band of light stretching across the heavens. This band was the edge-on view of the disk, the combined light of billions of stars lying in a relatively flat structure. When they looked perpendicular to this band, above or below the galactic plane, they saw far fewer stars. The sky in those directions was darker, more transparent. This asymmetry suggested that the galaxy was indeed flat, with most of its matter concentrated in the disk. This view was reinforced by studies of other galaxies. When astronomers looked at spiral galaxies similar to the Milky Way, they saw flat rotating disks with spiral arms. Some galaxies were seen face-on, showing their beautiful spiral structure clearly. Others were seen edge-on, appearing as thin, bright lines with dark dust lanes running through them. In both cases, the disk was the dominant feature. The message seemed clear. Spiral galaxies were disk-shaped objects. Whatever lay outside the disk was secondary, a sparse halo of old stars and perhaps some dark matter, but nothing that affected the galaxy's overall structure or evolution. This paradigm was further supported by theoretical considerations. The formation of a rotating disk made sense from a physics standpoint. As gas collapsed under gravity to form a galaxy, conservation of angular momentum would cause it to flatten into a disk. Stars forming from that gas would inherit its rotation, orbiting the galactic center in roughly circular paths within the plane. This was the natural outcome of the process, and it explained the structure of the disk beautifully. The halo, by contrast, seemed like a relic, a collection of stars left over from earlier stages of galaxy formation before the disk had settled. Within this paradigm, the vertical dimension of the galaxy was not considered very important. Yes, there were globular clusters orbiting above and below the disk, but they were viewed as separate objects, not really part of the galaxy's main structure. Yes, there were old halo stars moving in random orbits, but they were just a sparse population with little influence on the galaxy's dynamics. The real action, the star formation, the spiral structure, the evolution of the galaxy, all of that happened in the disk. If you wanted to understand the Milky Way, you studied the disk. The vertical direction was an afterthought. This paradigm influenced research in subtle but important ways. Observing time on telescopes is precious, and astronomers have to make choices about what to study. If the halo was seen as unimportant, few astronomers would propose observations aimed at studying it. Funding agencies, peer reviewers, and telescope allocation committees would be more likely to support projects focused on the disk, where the science seemed more interesting and the potential for discoveries seemed greater. This created a feedback loop. The less attention the halo received, the less we learned about it, and the less important it seemed. There were, of course, astronomers who did study the halo, but they were often seen as working on niche problems. Globular cluster specialists, for instance, were a relatively small community. They studied these ancient stellar systems in detail, measuring their ages, their chemical compositions, their internal dynamics. But their work was often viewed as tangential to the main questions in galactic astronomy. Similarly, astronomers who studied the kinematics of halo stars were addressing interesting dynamical problems, but these problems seemed disconnected from the bigger picture of how galaxies formed and evolved. The flat galaxy paradigm also affected theoretical work. Models of galaxy formation and evolution in the mid-20th century focused almost exclusively on the disk. Theorists tried to understand how spiral arms formed, how gas cooled and formed stars, how the disk's rotation supported it against gravitational collapse. These were important problems, and the models developed to address them were sophisticated and successful, but they largely ignored the halo. It was treated as a passive component, a fixed gravitational potential within which the disk evolved, rather than an active participant in the galaxy's life. The paradigm began to crack in the 1970s and 80s, as evidence accumulated that couldn't be easily explained within the flat galaxy framework. The discovery of dark matter was one key factor. Rotation curve measurements showed that galaxies contained far more mass than could be accounted for by visible stars and gas. This extra mass had to be in the halo, extending far beyond the visible disk. Suddenly, the halo was not just a sparse collection of old stars, but the dominant component of the galaxy in terms of mass. It couldn't be ignored anymore. Another crack came from studies of galactic chemical evolution. The metallicity, or abundance of heavy elements, varied systematically in different parts of the galaxy. Disk stars were relatively metal-rich, while halo stars were metal-poor. This suggested different formation histories, with halo stars forming early when the universe had not yet been enriched with heavy elements, and disk stars forming later from recycled material. But understanding this required thinking about the galaxy as a whole, including the halo, not just focusing on the disk. Observations of other galaxies also challenged the paradigm. X-ray observations revealed hot gas extending far above and below the disks of some spirals. Radio observations showed plumes and outflows, gas being expelled from the disk into the halo. These structures suggested that the halo was not a passive void, but an active region where gas flowed, where energy was transported, where the disk and the larger galaxy interacted. If other galaxies had active halos, why wouldn't the Milky Way? But paradigms are sticky. Even when evidence accumulates against them, they don't disappear overnight. Scientists are human, and humans are creatures of habit. We get used to thinking in certain ways, to asking certain types of questions, to using certain tools and techniques. Changing a paradigm requires not just new data, but a shift in perspective, a willingness to see familiar objects in new ways. This shift often happens gradually, driven by a combination of accumulating evidence, new observations that can't be explained by the old framework, and the entry of new generations of scientists who are not as invested in the old ways of thinking. The discovery of the Fermi bubbles in 2010 was a watershed moment. Here was a structure so large, so dramatic, that it could not be ignored or explained away. The bubbles extended 25,000 light-years above and below the disk. They glowed with gamma rays, evidence of energetic processes on enormous scales. They showed that something extraordinary had happened at the galactic center, something that had reshaped the halo. The flat galaxy paradigm simply couldn't account for them. To understand the Fermi bubbles, you had to think about the galaxy in 3 dimensions, to consider the vertical transport of energy and matter, to recognize that the halo was not passive but dynamic. Even then, the shift was not instantaneous. Some astronomers initially viewed the bubbles as a curiosity, an unusual feature that didn't fundamentally change our understanding of the galaxy. But as more data came in, as follow-up observations revealed additional structures in the halo, as computer simulations showed how galactic winds could shape these regions, the old paradigm became increasingly untenable. The Milky Way was not just a flat disk. It was a 3-dimensional system with complex vertical structure, shaped by feedback processes that connected the disk, the halo, and the galactic center. Looking back, it's easy to see the flat galaxy paradigm as a mistake, a failure to recognize the full complexity of the Milky Way. But that's not quite fair. The paradigm was based on the observations available at the time, and within its limitations, it was useful. It helped organize knowledge, guided research, and led to important discoveries about the disk's structure and evolution. The problem was not that it was completely wrong, but that it was incomplete. It emphasized one aspect of the galaxy, the disk, at the expense of others, and it created blind spots, regions that were understudied and undervalued. The opposition to thinking vertically about the galaxy was not overt or deliberate. There were no committees decreed that the halo should be ignored. Rather, it was a matter of emphasis and priorities. The disk seemed more important, more interesting, more accessible. The halo seemed obscure and difficult. And in science, as in other fields, the path of least resistance often determines where effort is directed. Overcoming this required not just new data, but new ways of thinking, a recognition that the overlooked directions, the space above and below, were just as important as the familiar plane. The history of the flat galaxy paradigm is a reminder that science is not a straightforward march toward truth. It's a human endeavor, shaped by assumptions, by the tools available, by social and institutional factors. Paradigms can be both useful and limiting. They help us organize our thoughts but can also blind us to possibilities. Progress often comes not from working harder within an existing framework, but from questioning the framework itself, from looking in directions others have ignored, from recognizing that the familiar view might be incomplete. The shift from viewing the Milky Way as a flat disk to understanding it as a 3-dimensional structure happened gradually, but by the early 21st century, the transformation was nearly complete. Astronomers had awakened to the importance of the vertical dimension, recognizing that the space above and below the disk was not an empty afterthought, but an integral part of the galaxy. This awakening was driven by new observations, new theoretical insights, and new tools that made it possible to probe the halo in unprecedented detail. It represented a fundamental change in perspective from two-dimensional thinking to three-dimensional thinking, from seeing the galaxy as a flat object to seeing it as a complex, layered structure with depth. One of the key drivers of this awakening was the availability of large data sets covering the entire sky. Projects like the Sloan Digital Sky Survey, which began in the early 2000s, imaged millions of stars and galaxies, creating a comprehensive map of the visible universe. By selecting stars based on their colors and brightnesses, astronomers could identify halo stars and trace their distribution across the sky. What they found was startling. The halo was not smooth and featureless, but filled with structure. There were streams, clumps, shells, and overdensities, remnants of smaller galaxies that had been absorbed by the Milky Way over billions of years. These structures could only be understood by thinking in three dimensions. A stellar stream, for instance, is a one-dimensional feature, a line of stars tracing an orbit through space. But that line exists in a three-dimensional volume, and understanding its shape requires measuring not just positions on the sky, but distances and velocities. As astronomers develop techniques for measuring stellar distances, using everything from parallax to spectroscopy to statistical methods, the three-dimensional structure of the halo came into focus. The streams wrapped around the galaxy in complex loops, each one tracing the path of a satellite that had been disrupted. The Gaia satellite provided a quantum leap in this capability. By measuring the positions and motions of over 1 billion stars with exquisite precision, Gaia allowed astronomers to reconstruct the orbits of individual stars. They could trace back where stars had been in the past and predict where they would be in the future. This revealed patterns that had been invisible before. Stars that appeared randomly scattered on the sky turned out to be moving together, members of coherent groups with common origins. The halo was full of such groups, fossils of ancient mergers preserved in the motions of their constituent stars. Three-dimensional thinking also transformed our understanding of galactic winds. Before, winds were often thought of as phenomena confined to the disk or the immediate surroundings of the galactic center. But observations in multiple wavelengths showed that winds extended far into the halo, reaching tens of thousands of light years above and below the plane. These winds carried energy and matter vertically, connecting different parts of the galaxy. They heated the halo gas, creating a hot atmosphere that surrounded the disk, and they carved out structures like the Fermi bubbles, vast cavities filled with energetic particles. Understanding these winds required thinking about the galaxy as an integrated system. Energy released in the disk or at the galactic center didn't just affect its immediate surroundings, it propagated through the halo, shaping its structure and influencing processes far away. Gas expelled from the disk could travel thousands of light years before cooling and falling back. This created a circulation pattern, a galactic fountain where matter cycled between the disk and the halo over millions of years. The fountain was invisible in any single observation, but by combining data from different wavelengths and different tracers, astronomers could piece together the flow. Computer simulations played a crucial role in the awakening. As computing power increased, it became possible to simulate entire galaxies in 3 dimensions, following the evolution of millions or even billions of particles over cosmic time. These simulations started with the distribution of dark matter in the early universe and followed how it collapsed under gravity, forming halos and filaments. Within these dark matter halos, gas cooled and condensed, forming stars. The simulations included the effects of supernova feedback, stellar winds, and black hole activity, showing how energy injected by these processes affected the surrounding gas. The results were revelatory. The simulations naturally produced galaxies with extended halos, populated by streams and substructures. They showed that feedback was essential for producing realistic galaxies. Without it, too much gas collapsed into the center, forming overly massive disks and bulges. With feedback, the gas was heated and expelled, regulating star formation and creating the diffuse halos observed in real galaxies. The vertical transport of energy and matter was not a minor effect, but a central process in galaxy evolution. These simulations also showed how galaxies grew over time through hierarchical assembly. Smaller dark matter halos merged to form larger ones, and the galaxies within them merged as well. Each merger left signatures in the halo, streams of stars following the orbit of the disrupted satellite. By studying these streams, both in simulations and in real galaxies, astronomers could reconstruct the merger history, identifying when and how the galaxy had absorbed its neighbors. The Milky Way's halo became a kind of archaeological site, preserving the record of its assembly. The awakening to three-dimensional thinking also changed how astronomers thought about galaxy classification. The traditional Hubble sequence, which classified galaxies as spirals, ellipticals, or irregulars based on their two-dimensional appearance, was incomplete. It didn't capture the full complexity of galactic structure. Two galaxies might look similar in projection, seen face-on or edge-on, but have very different halos, different amounts of dark matter, different merger histories. Understanding a galaxy required looking beyond its visible disk to the larger three-dimensional structure that surrounded it. This new perspective revealed connections between different areas of astrophysics. The study of the halo intersected with cosmology, because the halo's dark matter was related to the large-scale structure of the universe. It intersected with stellar astrophysics, because the halo stars were among the oldest in the universe and provided constraints on stellar evolution models. It intersected with high-energy astrophysics, because the Fermi bubbles and other structures in the halo were powered by energetic processes. And it intersected with galactic dynamics, because the halo's gravitational field shaped the motions of everything within the galaxy. The awakening also had practical implications for how astronomy was done. Multi-wavelength observations became essential. No single wavelength could capture the full complexity of the halo. Optical observations revealed stars. Radio observations traced gas. X-rays showed hot plasma. Gamma rays detected high-energy particles. Each wavelength provided a different piece of the puzzle, and combining them was necessary to see the whole picture. This required collaboration between different communities, between optical astronomers and radio astronomers, between X-ray observers and theorists, between simulators and data analysts. The development of new statistical and computational techniques was equally important. The data sets were enormous, containing billions of measurements. Extracting meaningful patterns from this data required sophisticated algorithms, machine learning, and careful statistical analysis. It required thinking about uncertainties, about biases in the observations, about how to test whether a feature in the data was real or just noise. The awakening to three-dimensional thinking was not just conceptual but methodological, requiring new tools and new approaches. Perhaps the most profound aspect of the awakening was the recognition that the galaxy was not a static object but a dynamic, evolving system. The halo was not a fixed backdrop but an active participant in the galaxy's life. It recorded the past through its stellar streams and chemical gradients, It shaped the present through its gravitational field and its reservoir of hot gas, and it would influence the future as infalling satellites continued to merge and as the galaxy's interaction with Andromeda drew closer. Three-dimensional thinking meant thinking not just spatially but temporally, recognizing that the structures we see today are snapshots of an ongoing process that spans billions of years. The awakening transformed our understanding of what lies above and below the Milky Way. It revealed a region that was complex, structured, and dynamic. It showed that the vertical dimension was not a void, but a space filled with matter, energy, and history. And it demonstrated that to truly understand the Milky Way, we had to see it whole, in 3 dimensions, as a galaxy embedded in a cosmic web, breathing matter and energy through its halo, shaped by its past and still evolving toward its future. All the observations, all the theories, all the simulations and models pointed toward a single profound realization. The Milky Way is not a static collection of stars, but a living, breathing system. It inhales and exhales, drawing in gas from the intergalactic medium and expelling it through winds. It exchanges matter and energy between its different components: the disk, the bulge, the halo, the galactic center, and the space above and below the disk is where much of this breathing happens, where the galaxy's circulation system operates, connecting the inside to the outside, the past to the present. This revelation changed everything. It meant that the galaxy was not just an object to be mapped and catalogued, but a process to be understood. A system with inputs and outputs, with cycles and feedback loops, with a metabolism. The concept of a breathing galaxy emerged from the accumulated evidence of galactic winds and gas flows. Observations showed that gas was constantly moving vertically through the galaxy. Some of it was hot, heated to millions of degrees by supernova explosions or shocks from the galactic center. This hot gas rose into the halo, buoyed by its own thermal pressure, creating plumes and bubbles that extended far above the disk. Other gas was cool, condensing from the hot halo and falling back toward the disk under gravity. This cool gas-fed star formation replenishing the disk's reservoir of raw material and sustaining the ongoing process of stellar birth. The analogy to breathing is apt. Just as lungs inhale oxygen and exhale carbon dioxide, exchanging gases with the environment, the galaxy inhales fresh gas from the intergalactic medium and exhales enriched gas through its winds. The inhaled gas is mostly pristine hydrogen and helium, material left over from the Big Bang. The exhaled gas is enriched with heavy elements, carbon, oxygen, iron, and others, created in the cores of stars and dispersed by supernova explosions. This exchange is not just passive diffusion but an active process, driven by energy released within the galaxy. The rate of breathing matters. If the galaxy inhales too quickly, accreting large amounts of gas in a short time, it can trigger a burst of star formation. This starburst heats the gas and drives powerful winds, which expel much of the gas back into the halo. The galaxy then has to wait for the gas to cool and fall back before star formation can resume. This creates a cycle, an oscillation between active and quiescent phases. If the galaxy exhales too much, expelling more gas than it accretes, star formation slows down or stops entirely, and the galaxy fades over time. Maintaining a balance, a steady breathing pattern, is what allows galaxies like the Milky Way to form stars consistently over billions of years. The Fermi bubbles are evidence of a particularly powerful exhalation. The event that created them, whether driven by the black hole or by a starburst, expelled a huge amount of gas and energy into the halo. This was not normal breathing, but more like a cough or a sneeze, a sudden violent release. The bubbles are still visible millions of years later, towering above and below the galactic center, glowing with the remnant energy of that event. Over time, they will fade and dissipate, and the galaxy's breathing will return to a more regular rhythm. But while they last, they remind us that the galaxy is capable of dramatic changes, that its breath is not always calm and steady. The circulation of gas through the halo also means that the disk and the halo are not separate systems but intimately connected. Stars forming in the disk today are made from gas that may have spent time in the halo, perhaps millions of years ago. That gas was expelled by supernovae, cooled in the halo, and fell back to the disk. During its time in the halo, it mixed with other gas, acquiring a different chemical composition. This mixing affects the properties of the stars that form, their metallicities, their abundances of specific elements. By studying the chemical compositions of stars in the disk, astronomers can learn about the history of gas circulation, about how efficiently the galaxy recycled its material. The breathing also affects the galaxy's dark matter halo. While dark matter itself doesn't interact with ordinary matter except through gravity, the motion of gas through the halo is shaped by the dark matter's gravitational field. Gas falls inward along the dark matter's potential wells and is expelled outward along the paths of least resistance. The dark matter provides the scaffolding, the framework within which the breathing occurs. Without it, the galaxy's breath would be chaotic, with gas escaping in all directions. With it, the flows are organized, channeled into structures like the Fermi bubbles that follow the galaxy's axis of rotation. Understanding the galaxy as a breathing system required integrating knowledge from many different areas. Stellar astrophysics provided information about how stars evolve and how they return matter to the interstellar medium through winds and explosions. Fluid dynamics described how gas moves under pressure, how it forms shock waves, how it cools and condenses. Thermodynamics explained how energy is transported and dissipated, how hot gas radiates away its energy, and how radiation heats gas. And cosmology set the context, showing how galaxies are embedded in a larger structure, how they accrete gas from filaments of the cosmic web, and how they interact with neighboring galaxies. Computer simulations of galaxy evolution began to include these processes explicitly. Modern simulations tracked not just the gravitational dynamics of dark matter and stars, but also the thermodynamics of gas, the cooling and heating processes, the effects of supernova feedback, and black hole winds. The simulations showed that galaxies without feedback, galaxies that couldn't breathe, looked nothing like real galaxies. They were too compact, too massive, with too many stars. But galaxies with realistic feedback, with breathing driven by stellar and black hole energy, reproduced the observed properties of real galaxies remarkably well. The breathing was not an optional detail but a fundamental process that shaped galaxy evolution. The revelation also extended to understanding the role of the galactic center. The supermassive black hole at the heart of the Milky Way was not just a passive object sitting there. It was a regulator, a valve that controlled the flow of energy through the system. When the black hole was active, it injected energy into the surrounding gas, heating it and driving winds that affected the entire galaxy. When it was quiescent, as it is now, the galaxy's breathing was driven mainly by stellar processes. But the black hole's potential for activity meant it could dramatically alter the galaxy's metabolism at any time, changing the rate and pattern of breathing. This perspective made the Milky Way seem less like a machine and more like an organism. It had structures analogous to organs, the disk where stars formed, the halo where gas circulated, the galactic center where energy was concentrated. It had flows analogous to circulation systems, the movement of gas up and down, in and out. And it had cycles analogous to metabolic processes, the conversion of gas into stars, the release of energy by those stars, the recycling of material. The analogy shouldn't be pushed too far. Galaxies are not alive in the biological sense, but it captured something important about their nature. They are not static objects, but dynamic systems, self-regulating through feedback, evolving over time. The breathing also connected the Milky Way to other galaxies. Every spiral galaxy with active star formation likely breathes in a similar way, cycling gas between its disk and halo. The details vary. Some breathe faster, some more slowly. Some have more violent outbursts, others more steady exhalations. But the basic process is universal. Even elliptical galaxies, which are no longer forming stars, show evidence of past breathing in the form of hot gas halos and X-ray emission. They stopped forming stars when they ran out of cold gas, when their breathing became shallow and they could no longer inhale enough material to sustain star formation. Looking at the Milky Way from this perspective, as a breathing galaxy, the space above and below the disk takes on new significance. It's not just where old stars drift or where dark matter accumulates. It's the galaxy's lungs, the region where inhalation and exhalation occur, where gas flows in and out, where the exchange with the larger universe happens. When we look up or down from the disk, we're looking at the mechanisms that keep the galaxy alive, that allow it to continue, forming stars, that connect it to the cosmic web and to the evolution of the universe as a whole. This revelation brought a sense of wonder. We live not in a cold, dead structure, but in a living, evolving system. The galaxy around us is in motion, circulating matter and energy on timescales far longer than human lifetimes, but nonetheless real. Every star we see formed from gas that cycled through the halo. Every element heavier than hydrogen was created in a star and dispersed through the halo before being incorporated into new stars and planets. We ourselves, the atoms that make up our bodies, went through this cycle. We are made of material that the galaxy breathed, that moved vertically through its structure, that participated in its metabolism. Understanding what lies above and below the Milky Way is, in a sense, understanding where we come from and how we came to be. There's something strange about the directions we've been exploring. Up and down, above and below. These words feel natural when we use them, as if they describe something fundamental about the universe. But in space, there is no true up or down. There's no absolute vertical, no fixed reference point that defines these directions. They exist only relative to us, relative to the disk of the Milky Way, relative to the plane in which we orbit. And yet, these arbitrary directions have revealed so much. They've shown us structures we never expected, processes we didn't understand, a history we couldn't have reconstructed without looking in these supposedly meaningless directions. What does that say about the nature of the universe, about how we understand it, and about our place within it? The disk of the Milky Way defines our vertical axis simply because that's where we live. We orbit within the plane, moving with billions of other stars in roughly the same direction. It's natural for us to think of the plane as horizontal, as the baseline, and everything perpendicular to it as vertical. But from another perspective, from outside the galaxy, or from another galaxy entirely, those directions would be arbitrary. A hypothetical observer in Andromeda wouldn't see our up as anything special. They would see the Milky Way at an angle, its disk tilted relative to their own, and they would define their own vertical based on their own disk. This relativity of direction is a reminder that much of what we consider fundamental is actually contingent, dependent on where we are and how we're oriented. In everyday life, Up and down are defined by gravity, by the pull of Earth beneath our feet. Up is away from the ground, down is toward it. But step into orbit, and those definitions lose their meaning. Astronauts floating in the International Space Station don't have an up or down. They orient themselves relative to the station, choosing which surface to call the floor, but it's an arbitrary choice. The universe doesn't care. And yet, the directions perpendicular to the galactic plane are not entirely arbitrary. They're special because of physics, because of how the galaxy formed and how it's structured. The disk is flat because of rotation, because angular momentum causes matter to settle into a plane. The directions perpendicular to that plane are the directions along the rotation axis, the directions where centrifugal effects are minimal and where matter is free to move under gravity alone. This makes the vertical directions dynamically different from the radial directions, different from moving in or out within the plane. It's along these vertical directions that galactic winds blow most freely. In the plane, the disk's gravity holds gas tightly, making it hard for winds to escape. But above and below, the density is lower, the resistance is less, and winds can expand more easily. This is why the Fermi bubbles are elongated vertically, stretching farther in those directions than horizontally. The physics of the system picks out the vertical as a preferred direction, even though there's no absolute vertical in space. The structure creates meaning, where the universe itself offers none. This raises a philosophical question. How much of what we see in the universe is imposed by its structure, and how much is imposed by our perspective? The Fermi bubbles are real structures, independent of whether we observe them. Their shape, their energy, their effects on the surrounding gas, all of these are physical facts. But our description of them as being above and below, our choice to study them by looking perpendicular to the disk, these are choices shaped by our location and our orientation. A different observer in a different location would describe the same structures differently. This interplay between objective reality and subjective perspective runs through all of astronomy. We describe the universe using coordinates, systems like right ascension and declination, or galactic latitude and longitude. These systems are convenient, but they're human constructs. The universe doesn't come with coordinates marked on it. We impose them, choosing reference points and orientations that make sense from our perspective. The galactic plane is a natural reference because it's where we are, but it's still a choice. What we've learned by looking up and down, by exploring the vertical dimension of the Milky Way, is that direction matters. Where you look determines what you see. For centuries, astronomers focused on the disk because that's where the brightest stars were, where the most obvious structures existed. The halo was faint and diffuse, easy to overlook. But once we started looking carefully in those directions, once we had the tools to detect faint signals and the patience to map large areas of the sky, we discovered that the halo was not empty at all. It was full of information, full of structures that told the story of the galaxy's past and present. This is a lesson that extends beyond astronomy. In any field, what you discover depends on where you look. If you focus only on the obvious, the bright, the easily accessible, you'll miss the subtle, the hidden, the overlooked. Sometimes the most important insights come from looking in directions others have ignored, from asking questions that seem tangential or unimportant. The space above and below the galactic disk seemed like a backwater, a region of secondary importance, but it turned out to be central to understanding how the galaxy works. The meaning of up and down, then, is not just about physical direction. It's about perspective, about the choices we make in how we explore and understand the universe. It's about recognizing that our viewpoint shapes what we see, but also that physical reality constrains what's possible. The galaxy's structure creates real distinctions between different directions, even if those distinctions are relative to a particular reference frame, and our exploration of those directions reveals truths that are independent of our perspective. Truths about how matter and energy flow, how galaxies evolve, how the universe is put together. There's also something humbling about this. We live inside the disk, embedded in the plane, and for most of history, we didn't even realize there was a halo. We thought the galaxy was just the band of light we saw stretching across the sky. It took centuries of careful observation, measurement, and theory to understand that we were looking at a cross-section of something much larger. And even now, with all our instruments and our knowledge, there are certainly structures and processes in the halo that we haven't detected yet, questions we haven't thought to ask, directions we haven't thought to look. The vertical dimension of the Milky Way also reminds us of scale. The distance from the disk to the top of the Fermi bubbles is 25,000 light years. That's an almost incomprehensible distance. Light, travelling at 300,000 kilometers per second, takes 25,000 years to cover it. If you could somehow travel at the speed of light, starting from the galactic plane and heading straight up, you would pass through the bubbles over millennia, watching them slowly transition from the dense, energetic interior to the shock-heated edge to the cooler halo beyond. The scale is so vast that it defies human intuition, and yet that vast distance is only a fraction of the galaxy's full extent. The dark matter halo reaches out to hundreds of thousands of light years, 10 times farther. The stellar streams wrap around the galaxy in loops that span similar distances. When we talk about what's above and below the Milky Way, we're talking about a volume that dwarfs the visible disk, a space so large that it contains most of the galaxy's mass, even though it's mostly invisible. Our sense of scale, shaped by everyday experience, by the distances we can walk or drive or fly, is utterly inadequate for grasping these cosmic dimensions. But perhaps that inadequacy is part of the point. The universe is under no obligation to fit within our intuitive understanding. It operates on scales far larger and far smaller than we can directly perceive. Learning about it requires extending our senses through instruments, our intuition through mathematics, our imagination through models and simulations. The space above and below the galaxy is a place we can never visit, but we can study it, map it, understand it. We can know it exists, know what it contains, know how it affects the rest of the galaxy, even though we'll never experience it directly. This reflects a deeper truth about science. It's not just about cataloguing what's out there. It's about understanding relationships, patterns, processes. It's about seeing how different parts of the universe connect to each other, how they influence each other, how they form a coherent whole. The disk and the halo are not separate things but parts of a single system. Energy flows between them, matter cycles through them, and understanding either one requires understanding both. The meaning of up and down is that they connect us to the rest of the galaxy. They show us dimensions we didn't know existed. They reveal the whole where we previously saw only a part. In the end, perhaps the meaning of up and down is simply this: they are directions that led to discovery. By looking in those directions, we found structures that changed our understanding of the Milky Way. We found evidence of the galaxy's violent past, its dynamic present, its breathing metabolism. We found dark matter halos and stellar streams, hot gas and gamma-ray bubbles, ancient stars and ongoing winds. We found a galaxy far more complex and interesting than the flat disk we started with. And we found that our home, this spiral galaxy in which we orbit, is not a static island but a living system, connected to the universe around it, evolving over cosmic time. The directions we call up and down may be arbitrary, defined by our location and orientation, but the discoveries we made by looking in those directions are real. They exist independent of our perspective, and they remind us that the universe always has more to reveal, if we're willing to look in new directions, to question our assumptions, to explore beyond the familiar. What lies above and below the Milky Way is not just empty space. It's a dimension of the galaxy we're only beginning to understand, full of mysteries still waiting to be uncovered. If you could step back now, far enough to see the entire Milky Way at once, far enough that the disk appears as a single glowing spiral and the halo as a faint sphere around it, you would see something remarkable. You would see that the galaxy doesn't end where the light fades. It continues, extending in all directions, but especially above and below. The visible disk, the bright band we see from Earth, is just the densest part of a much larger structure. The galaxy reaches upward and downward far beyond what our eyes can perceive, blending gradually into the intergalactic medium, connected to the cosmic web. There is no sharp boundary where the Milky Way ends and empty space begins. The dark matter halo extends hundreds of thousands of light years, gradually thinning until its density merges with the background density of the universe. The gas in the halo does the same, becoming more and more diffuse until it's indistinguishable from the intergalactic medium. Even the stars, scattered thinly through the outer halo, fade into the general population of intergalactic stars, those wanderers that were ejected from galaxies and now drift through the voids. The vertical dimension of the galaxy is infinite in the sense that it has no clear edge. It extends as far as you care to measure, fading gradually but never stopping abruptly. This continuity is one of the most profound things we've learned about the universe. Nothing is truly isolated. Everything connects to everything else through gravity, through the flow of matter and energy, through the shared history of cosmic evolution. The Milky Way is not a separate entity floating in empty space. It's a concentration of matter within a larger structure, a node in the cosmic web, surrounded by filaments of dark matter and gas that link it to neighboring galaxies. The space above and below the disk is where these connections are most visible, where the galaxy's atmosphere blends into the intergalactic medium, where its influence fades but never truly disappears. When we look upward from the disk, we're looking through layers. First, the thin layer of the disk itself, about 1,000 light years thick, where most of the stars and gas reside. Then the thicker layer of the inner halo, a few thousand light years above the plane, where hot gas glows in X-rays, and the edges of the Fermi bubbles mark the boundary of recent outflows. Beyond that, the stellar halo extends outward, gradually, thinning, dotted with ancient stars and globular clusters tracing long elliptical orbits. And farther still, the dark matter halo dominates, invisible but massive, its gravity shaping everything within it. Each layer tells part of the story. The disk records the present and the recent past, the ongoing process of star formation and stellar evolution. The inner halo records more distant events, the outbursts and winds that reshaped the galaxy millions of years ago. The stellar halo preserves the ancient past, the mergers and accretions that built the galaxy over billions of years. And the dark matter halo provides the foundation, the unchanging gravitational framework that allowed all of this to happen. Together, these layers form a three-dimensional archive, a record written in matter and motion that extends vertically through the galaxy. The same is true when we look downward. Below the disk, we find mirror images of what's above. The Fermi bubbles extend symmetrically, one lobe above, one below. The hot gas forms a roughly spherical atmosphere centered on the disk. The stellar halo wraps around the entire galaxy, indifferent to our notions of up and down. And the dark matter halo extends equally in all directions. A sphere, or perhaps a slightly flattened ellipsoid, depending on how the galaxy formed and what mergers it experienced. This symmetry is not perfect. There are asymmetries, regions where the density is slightly higher above than below, or vice versa. These asymmetries reflect the galaxy's history, the specific sequence of mergers and interactions that shaped it. They're like scars, marks left by events that didn't affect the galaxy uniformly. By studying these asymmetries, astronomers can learn about individual events, about which satellite fell in from which direction, about how its mass and trajectory perturbed the existing structure. But despite the asymmetries, the overall picture is one of continuity. The galaxy extends smoothly in all directions, with no fundamental difference between above and below. If we lived in a different part of the disk, or if we were oriented differently, we might call different directions up and down, but we would find the same structures, the same processes, the same layers extending perpendicular to the plane. The vertical dimension is not unique. It's simply one of the dimensions we've chosen to explore, and it has revealed the galaxy's depth. As we reach the end of this journey, it's worth reflecting on what we've seen. We started with the Fermi bubbles, those enormous structures that tower above and below the galactic center. Glowing with gamma rays, we traced back their origin to an ancient explosion or outburst, an event powerful enough to reshape the halo. We explored the dark matter that dominates the galaxy's mass, invisible but essential. We followed stellar streams wrapping around the galaxy, remnants of smaller systems that were absorbed. We watched gas cycling between the canvae, disk and the halo, part of the galaxy's breathing, and we recognized that the Milky Way is not a flat disk but a three-dimensional system, dynamic and evolving, connected to the larger universe. All of this was hidden above and below the plane, in directions we barely noticed for most of human history. The bright band of the Milky Way across the night sky is beautiful and awe-inspiring, but it's only a small part of the whole. Most of the galaxy, in terms of volume and mass, lies in the directions perpendicular to that band. By learning to see the galaxy in 3 dimensions, by looking up and down, we've discovered its true nature. What lies above and below the Milky Way, then, is not a simple answer. Its dark matter halos and stellar streams, hot gas and gamma ray bubbles, ancient stars and magnetic fields, inflows and outflows, history and ongoing evolution. It's a complex layered structure that extends far beyond the visible disk, fading gradually into the intergalactic medium, but never truly ending. It's the galaxy's breathing mechanism, the region where energy and matter are exchanged with the larger universe. And it's a reminder that the cosmos is deeper and more intricate than we can grasp from our small corner of it. As you drift back now, in your mind, from that distant vantage point where you could see the whole galaxy, you return to Earth, to the solar system, to our place within the disk. The night sky above still shows the familiar constellations, the band of the Milky Way arcing overhead. But now, you know what's really there. You know that above and below that band, invisible to your eyes, there are structures stretching for tens of thousands of light years. You know that the galaxy extends far beyond what you can see, that it has depth and complexity, that it's breathing and evolving. You know that you live not in a flat disk, but in a 3-dimensional cosmos, connected to everything around it. The space above and below the galaxy is not empty. It's not a void, it's part of the galaxy itself, as essential as the disk, perhaps more so. It's where the galaxy keeps its memories, in the form of ancient stars and stellar streams. It's where the galaxy regulates itself, through the cycling of gas and the feedback from stars and black holes. It's where the galaxy connects to the universe, exchanging matter and energy with the intergalactic medium and the cosmic web. Understanding this space, this vertical dimension, is understanding the galaxy as a whole. So the next time you look up at the night sky, remember that you're seeing only a fraction of what's there. The band of the Milky Way is one dimension, a cross-section through a much larger structure. Perpendicular to that band, above and below, the galaxy continues, reaching out into space farther than light can travel in tens of thousands of years. That space is filled with wonders, ancient and modern, visible and invisible, energetic and serene. It's the galaxy's hidden dimension, the vertical expanse that defines its shape and drives its evolution. And in that space, in those overlooked directions, we've found not just structures, but understanding. We've learned that galaxies are not static objects, but dynamic systems. We've learned that they breathe, cycling matter between their different components. We've learned that they have histories, recorded in the motions and compositions of their stars. We've learned that they're connected to the larger universe, part of a cosmic web that extends across all of space. And we've learned that looking in new directions, asking new questions, exploring beyond the familiar, always reveals more than we expected. The infinite vertical of the Milky Way extends above and below us, a dimension without end, fading gradually into the cosmos but never truly terminating. It's there, surrounding us, part of the galaxy we call home. And as we've explored it, we've discovered that the galaxy is far more than we imagined. It's deeper, more complex, more dynamic, more alive. It's a breathing system, an evolving structure, a record of cosmic history, and a participant in the universe's ongoing story. What lies above and below the Milky Way is, in the end, the galaxy itself, seen whole, understood in 3 dimensions, revealed in all its hidden glory. As you let these thoughts settle, as your breathing slows and the day fades into night, you can rest knowing that you're part of this vast structure. Every atom in your body was once part of the galaxy's vertical circulation, cycled through the halo, enriched by stars, returned to the disk. You are made of the same matter that flows above and below, and you exist within the same gravitational embrace that holds the entire system together. The galaxy surrounds you, extends above and below you, and continues far beyond where your eyes can see or your mind can reach. And in that endless vertical expanse, the Milky Way breathes, evolves, and carries us all through the cosmos.